We were sparks on quiet streets, two hearts finding where to meet. But life pulled us apart, left me talking to the dark. If I called you tonight, would it feel the same? Or have we both moved on to different names? Take me back to the start, before the quiet and the scars. When the world felt small and your hands felt warm. Take me back to the start, if only for a moment. I've been up since 3, scrolling back over.
Welcome to Let's Get to the Marks. Going to go through some revision for the chemistry paper 2 tomorrow. So what we're going to do, I haven't prepared any nice slides or anything. We're going to do a little bit of content followed by exam questions. We're going to go through each topic, okay? So yeah, let's go. I hope you're all doing well. I'm absolutely cream crackered. Well, we're going to start with rates of reaction, but before we're going to get into some rates of reaction. So yeah, what can I say? Well, oh my gosh. Yeah, we don't want this. This ain't rates of reaction. We're going to start with rates of reaction. I'm going to go through the content and then we'll go through it. But let me give you just a couple of little questions. Let me find some rates of reaction questions. Hold on. Hydrocarbons. Bada bada bing, bada bada bong. Hey, rates of reactions. I knew we'd get there in the end. So we're just going to start with some multiple choice and then I'll go through some content and give you some long form questions. All right, guys, little warm up. Here we go. What? Yep, I'm feeling like that lady, very tired right now. Anyway, let's go. Couple of rates of reactions. I'll go through the content after. So just to test you guys up to the kind of things you might get multiple choice wise. These are all from previous exams, whether it's combined or triple. I will point out when something is not relevant to combined science. So student A investigated the effect of the particle size of manganese dioxide on the rate of reaction. So student A is trying to investigate how particle size affects rate of reaction, and rate of reaction is the first topic I'm going to go through. This is the method used. Measure 25 centimeter cubed of 0.3 mole per decimeter hydrogen peroxide solution into a conical flask. Add a spatula of fine manganese dioxide powder. Ooh, nice and fine. Measure the volume of the gas produced every minute for 10 minutes. Repeat steps 1 to 3 with some coarse manganese dioxide lumps. Method A. The method student A used did not give valid results. What 2 improvements could student A make to give valid results? We want valid results. What didn't student A control very well? Here. So, if we have a little look, did they control the volume? Yeah, look. They used 25 centimeter cubed the volume of hydrogen peroxide. That's cool. That's good. They were changing particle size, but they wanted to change particle size. That was their independent variable. That's what they were changing. So coarse and fine makes sense because they were changing the particle size. They controlled the conc of hydrogen peroxide. So what is it they didn't do? Add a spatula. Is that very accurate? Adding a spatula of manganese dioxide. That's like saying add a teaspoon. What could they have done to make that much more valid? And measure the volume of gas produced every minute for 10 minutes. So what could they do to improve the validity? Measure the increase in mass of the conical flask and contents. Measure the volume of gas produced every 2 minutes. Place the conical flask in a water bath at a constant temperature. I reckon constant temperature is a good one. And it doesn't, that's just increasing the conc. They don't need to change, decreasing the conc. They don't need to change the conc. Use 1 gram each time. So what we're saying is keep the mass the same and keep the temp the same. So you're keeping the amount the same and the temp the same. Don't forget, for rates of reactions, there are 5 things that affect the rate of reaction. Do you remember the 5 things that affect the rate of reaction? You've got catalysts, which lower the activation energy, therefore speeding up the reaction. They provide an alternative pathway or an alternative route, lowering the activation energy. You have concentration. I'm just writing conc. By the way, pressure is the same as concentration, but it's for gases. You have surface area. You have temp. I think that's it there. That's it there. So you've got catalyst, temp, concentration, surface area. You might say, well, why do I have to keep the mass the same? It's kind of like for solids. If you're using solids, the mass is almost like the concentration for the solid. Okay. Okay, let's go. What about this next one? We'll just have a little look. The student changed the investigation so the mean time taken to collect 20 centimeter cubed of gas was greater. All right, if you change the investigation so it takes you longer to collect some gas, what 2 changes would you need to do to increase the time? You're not increasing the rate. Rate is amount over time, so you've actually slowed the rate down. They're really asking you, how did they slow their experiment down? What do we reckon? Hey, Petrovich is back. It's Petro. Yay. Yes, so if we want to slow the rate of reaction down, we're going to use a lower temperature and use a lower concentration of sulfuric acid, and that would slow the reaction down. Okay, nice. These ones, yeah, are no good. Okay, let's get into a little bit of theory on the rate of reaction, and then I'm going to give you a long form question on that. So let me give you a little bit of theory on the rate of reaction, and then I'll give you a long form one. So I'm going to run through what you need to know for rates of reaction. This is one of the 6, 7, 8, 9, 10, one of the 5 topics you've got to know. So rates of reaction. You might want to grab a pen and make some notes. I'm going to go get my pen. Oh my gosh. Woo. Alright folks, do me a big favor, make sure you hit the like. So that would be most nice of you if you hit the like. It'd be wonderful.
If you push the button.
Like me.
Would you like it?
Like.
Do it! Do it!
Do it. Okay, let's do this rates of reaction business. Okay, so reactions, yes. So first of all, you need to know about rates of reactions. Get the mouse out of the way, move the paper aside. So, come on T, sort it out pen. Just my pen's got to warm into this. Come on pen, get into this. I guess that is pushing on that. And that is no good. Alright, let's go down here then. Pen just, it's being a brute to me today. Right, rates of reaction. So what do we need to know? Here are the 5 factors once again. So if you need to make a note, 5 factors affecting rate. Now, when you do an investigation of rate, you may get a 6 marker on plan an investigation to investigate particle size on the rate of reaction, something like that. That has come up in the past. We're going to look at like 2 long form questions after we make these notes. So 5 factors affecting rate. They're going to be, once again, just to run through, you've got a catalyst. How does a catalyst affect the rate? It lowers the activation energy. You can also say provides an alternative route, doesn't get used up. The best catalysts are transition metals, nickel, platinum, copper, iron. 5 factors affecting the rate. We've got surface area. So surface area affects the rate. How does it affect the rate? More particles available for collisions. Then what else we got? We got concentration. Now, concentration, how concentration affects the rate is a 2 marker. So concentration, you need to say more particles. So you have to say more particles or reactants in same volume. That's 1 mark. More particles in the same volume. What does that do? That, I'm going to put an arrow for increases because I want to cut down on my writing so my wrist don't break. That increases, and this is a key word you have to say. So this is very, very important if you're answering and explain why the rate went up. If it says the word explain, you need to say increased frequency of successful, oh my gosh, I can't spell, successful collisions. Okay, that was disgusting. Now the hardest one that I haven't put there, by the way, pressure is exactly the same as that explanation, but temperature, I've not left myself any room because I'm a bit of a bell piece. So what I'm going to do, temperature's over here, and temperature is different to concentration. There are 3 key points you need to make about temperature. So increasing temp increases rate. If decreasing temp decreases rate. Why is this? We need to say more KE. Hopefully you know what KE means. It's more kinetic energy. So we're going to say more. There's 2 reasons for temperature. More particles have energy above AE. What do I mean by that? So imagine increasing the concentration is like a teacher saying to 20 of you in the class, run around the class. You start banging into each other, right? If I put another 20 people in the class, there's now 40 in the class, but you're all running at the same speed. You have to move at the same speed. I've doubled the chance of you banging into each other. Now, maybe only 5% of those will have a successful fight at the end of banging into each other. So if there's 40 people in there, we've doubled the amount of people who are going to have a successful collision. However, with increasing the temperature, you're not increasing the amount of particles, you're making people run faster. Now this changes because this means that you get more collisions because people are going faster, which I'm going to add there, more frequent collisions, but also more energetic collisions. Means when you do collide, it's harder, okay, because they're moving faster. So we say they have energy above the activation energy. You actually change the amount. More particles have energy above the activation energy. That doesn't happen with concentration. So we're going to say, again, we just want to cover ourselves, increase in frequency of successful collisions. All right, cool. Now, what else about rate do you need to know? So there's 3 ways to measure the rate of reaction. The rubbishest way to measure the rate of reaction, that's supposed to be an eyeball, is to look at a conical flask, get a sheet of card underneath, put a black cross on the card, and then what happens is you put like your reactants in here. Now the reactants are normally sodium thiosulfate and whatever else, acid, go in there. And what happens is as they react, oh my days, come on. As they react, they're going to go cloudy and the cross will disappear. What you can do, as we always do with rate of reaction, you can have like a stop clock. Check out the level 4 artwork, bro. You can have a stop clock timing that. How long does it take for the cross to disappear? So we call this disappearing cross. Obviously, this is not the most accurate way, but you may get given an experiment to comment on disappearing cross. Why is it not accurate? Well, each person's eyesight is different. Each person will see the cross disappear at a different time. So this is subjective. What does that mean, subjective? It means it relies on human eyesight, so it's gonna be very variable. So that's not the best way to measure the rate of reaction. A slightly better way to measure the rate of reaction, you're always going to need time, guys, so they might ask you, what do you need to measure the rate of reaction? Check out that conical flask. Absolute incredibilis. Right, we're going to put a bung in here to stop the gas escaping, and then we're going to put a little syringe on the end like this. I will get through every topic, okay, so don't panic. You're like, no, sir, you've not covered volcanoes yet. I'm going to cover it. Okay, so we put the reactants in here, and I will address the chat in a minute, but while I'm doing this, I ain't going to be able to address the chat. So reactants go in here, off come the bubbles. Notice my delivery tube is above the liquid. That's very important. They might catch you out with that. If you put this tube in the liquid will get sucked into this. This is a gas syringe, so we're going to measure the volume of gas coming off. Does anybody know in the chat why, again, this is not the most accurate way? It's better than that because you're getting a quantitative measure that is not subjective. You're getting an actual volume of gas. But why? What is the problem? There's an issue here with this. Anyone know what the issue with the bung is? So like I might be recording here and seeing how long it takes. Yes, gas escapes when you put the bung in. So if you put the bung in, gas escapes. It's not quite as accurate. It will never be perfect. As soon as your reactants go in, they start reacting. There is a way you can float one of the reactants in a little container and then put the bung in and then tip them and then they both mix. You can do it like that. So that is one way, but there's a little bit less accurate. Now the most accurate way, and watch out for this because this is a common one that they've tricked people and people always flop on this one. The most accurate way is to measure the mass. So you instead of collecting, this is collecting volume of gas over, and you're going to do volume of gas over time. This is just going to be 1 over T. You're going to do 1 divided by T time for this. Why 1 divided by time? You're not collecting anything. You're just saying when it goes cloudy. This one, you're going to do the volume of gas. So like if I collect 25 centimeter cubed over time, I'm going to do 25 over 30, gives me the rate. And with this one, you're going to place the conical flask on here, and you are going to measure the loss in mass. Now, because it's bubbling gas, it's going to lose mass. Now, guess what? That's actually great because we don't need to put a bung in. We're actually measuring how quickly the mass goes down. And that means if you plot mass against time, this might look unusual to you, but it's going to look like that, okay? So the rate of reaction is the mass is going to go down over time, okay? That doesn't mean the rate of reactions is necessarily decreasing unless it starts to flatten out. Now with this one, again, you're going to need the stop clock and you're going to need to record like time, and you're going to do mass over seconds. So you're going to get your rate in mass over seconds. Cool. Now very good. Liz Lucy, that's the bit I wanted to come to. You've mentioned about the cotton ball. Cotton wool. Loads of people, if they ask you what is cotton wool for, if this comes up tomorrow, it's a 1 marker. It's come up, it doesn't come up often, but it's come up like twice before. What is the cotton wool for? So many people say to stop the gas escaping, but hold on, we want the gas to get out. We want the gas to get out because we're measuring how quickly it goes down in mass. It's actually to stop your acid spitting out and you losing mass that wasn't a gas, that was unreacted reactants, to stop your metal or your acid or your calcium carbonate from spitting out. So you want to say the cotton wool prevents reactants from spitting out. It doesn't prevent the gas coming out. All right, don't spam up the chat, people. Don't spam up the chat. Don't spam up the chat. I am going to go through everything. If you spam up the chat, you get rinse out. I'm going to have to boot you out if you spam up the chat. Okay, let me just have a quick look if I've missed anything out. Rates of reaction. So remember that particles must collide to react. Remember that catalysts lower the activation energy that particles need to react. They provide an alternative route. Remember that increasing concentration increases the number of particles in the reaction, and therefore there are more collisions, so there are a higher number of successful collisions. Remember that increasing the surface area makes more particles available, so more collisions. And increasing the temperature is the biggest one with the most marks, because you increase the kinetic energy, so the particles move faster, so they have more frequent collisions, but also they have more energy, so the particles react with energy above the activation energy, meaning there are more successful collisions as well. All right. We're going to have a look at some questions on this. And the last couple of things I just want to say to remember for you guys. Remember that all rates of reaction are quickest at the start. So why is it if I measure rate, if I do rate of reaction against time, why is it that they're always steepest at the start? Why is the rate of reaction steepest at the start? So the rate of reaction is steepest at the start because there are more reactants. No, more reactants at the start. More reactants at the start. Yeah. As they carry on reacting, as they react, they become products and they'll no longer react. Like acid and base make salt and water. The salt and water don't react together. So the rate of reaction will naturally decrease because you're getting less collisions. All right, peeps, we're about to do a couple of questions on rate of reaction, and then we're going to get off of rates of reaction. So we're going to do about 10 minutes of rates of reaction questions, and then we have done that, and we're going to go on to the next chapter. Well, no, the next part of this chapter, which is Le Chatelier's principle, irreversible reactions, equilibria. Okay, so the student concludes that the rate of reaction is greater when the concentration of acid is higher. They're right. Why is the rate of reaction greater when the concentration of acid is higher? So there are more particles in the same volume. Boom, that's what a higher concentration is. Just remember the opposite of that. Lower concentration, less particles in the same volume. We're not affecting the surface area. The particles don't have more energy. That's only if you increase the temperature, and they won't be moving faster unless you increase the temperature. Okay, so it's these two here. More collisions per second, therefore. Awesome. Hydrogen peroxide molecules collide with manganese dioxide particles during the reaction. Why does fine manganese dioxide produce a higher rate of reaction? Why is fine better than coarse? Why does fine react faster than coarse? Yeah, fine powder has a larger surface area. Excellente. Fine powder has a larger surface area. Very good, very good. Okay, I'm not going to do that yet. That's equilibria. So before I do that, we're going to do a couple of long answer questions on rate of reaction. Then we're going to do equilibria. I know some people are like, getting too excited and they want to get on with the rest of the topics, but I'm just going to make sure that if you get one of these coming up, you are all right for it. So we're going to hit with, where's my rate of reactions? There it is. Lovely jubbly. All right, let's have a go at that. Bish bash bosh. Okay. Okay, what is that? What is that? What am I saying? What am I saying? 1.5. Let me give you this one to start. All right, we're going to do like 3 rates of reaction written questions now. We've done some multiple choice, and then we're going to smash on. I'm not going to get you to plot a graph. Let's not do a graph. Graph is long. I can't be putting, unless people want me to plot a graph. If they want me to plot a graph, I can. I will talk about a graph quickly about tangents and whether you have to do a tangent. All right, let's look at this one. Temperature also affects the rate of reaction. Explain how increasing temperature affects rate of reaction. Look at that. It's 3 marks. Can you get all 3? In the chat, put your 3 things that you think you would put to try to get the 3 marks. Talk about particles and collisions. So once I've finished with, we're going to do equilibria after rates of reaction. And once I've finished with that, we will do, once I finish with the old equilibria, we will do organic chemistry, hydrocarbons and all of that business. So that's coming up after, and then it will be chemistry in the atmosphere. So okay, so we've got some people saying increased kinetic energy. You'll get 1 mark for that. The particles of higher kinetic energy, yes, that's more mark. So more successful collisions, yes, more frequent collisions. We also want to say the collisions have greater energy than particles have more energy, and it's better to say they have energy greater than the activation energy. Just try to say that. All right, is everyone cool with that? I'll put the answer up if you want to know, because good chance of something like this. This is the most common one for them to ask about. Is this or concentration normally? So we want to say, by the way, you can't write KE, more kinetic energy. Probably say mark to say faster, moving. So more frequent collisions. I probably should put successful. Oh my god, what is that? Is that supposed to say frequent? Jeez. Collisions. More particles. And this is my shorthand way of saying have energy. And then I'm going to say above activation energy. So more particles have energy above the activation energy. Anyway, that's my 3 things. It's written really badly. I know what you're thinking. Right, let's go. Let's do one more rate, then we'll move on. One more rate, then we'll move on. Let's have a look at this one, see what this one's got to say for itself. What is that? Yeah, okay, cool. All right, we're going to do one more rate of reaction here, peeps. So, maybe, unless you guys want to do an extra rate of reaction, I think that we're all rated out. So let's smash this on. Bish, bash, bosh. It's going to go black. Da-da. No, I don't know why I just clicked on the little Microsoft shopping icon. That's annoying. Oh my god, rates of reactions is a topic which is annoying to do online. And it's annoying to do online because it has so many bloody graphs. Excuse my language. OMG! That's painful. Normally they're going to get you to draw on this as well. Okay, can't even read that. Never mind. I will talk you through it. All right, now we've got a 5 fat marker on this, but I'm going to do that one after. So, right, this is the last one on rate. So, here we go, people. A student investigated how the change in concentration affects the rate of reaction between zinc powder and sulfuric acid. The equation for the reaction is Zn solid plus H2SO4 aqueous goes to ZnSO4 aqueous plus H2 gas. This is the method used. Pour 50 centimeter cubed of sulfuric acid, concentration 0.05 mole per decimeter, into a conical flask. Add 0.2 grams of zinc powder to the conical flask. Put the stopper in the conical flask. Measure the volume of gas collected every 30 seconds for 5 minutes. Repeat 1 to 4 with sulfuric acid concentration of 0.10 mole per decimeter. Figure 8 shows the apparatus used. You know what that is. What did the error did they make? Who's got the error? Anyone got the error? He put the gas syringe in the reactants. Brilliant. Whoever said that? Boom. Well done. Have a look at that syringe. That's not good, is it? That's bad. So well done if you got that. Boom. Yeah, so, yes. Look. What's going to happen here is this liquid is going to get sucked up into there. You want to collect the gas. So really, that should be stopping about there, the tube. It should be collecting the gas, not collecting the liquid. So, tube in liquid or in solution, whatever. You get the idea. Explain why the lines of best fit on figure 9 become horizontal. Why do you think the volume of gas becomes horizontal after a certain amount of time? 2 fat marks. Who can get the marks? Why does the rate of reaction stop? You're absolutely right. One of the reactants has run out, right? So reactants used up, no more gas being produced. So no more hydrogen is coming off, no more hydrogen gas coming off. Remember, that's hydrogen that's coming off. We can tell it's hydrogen gas because it says so right up there. So it means one of our reactants has run out, either our acid or our metal. So reactants are used up, no more gas produced. How does figure 9 show the zinc powder reacts more slowly with 0.05 than with 0.1? So just to clarify that for you, this is the 0.1. This is the 0.05. How does the graph visually show you for 1 mark that it reacts more slowly? Thank you. That's a great answer. Best the pro. It is less steep. So line is less steep. You could say smaller gradient, shallower gradient, etc. Yes, produces less gas over the same amount of time, but they kind of want to say, how does it show that? How does the line show that? Listen, this next bit is going to be a hard one. No diddy. So I'm going to show you this next one. Hold on, peeps. No! That's not what I wanted. OMG. Right. This is still part of the same question, so we're going to look at this. It's a 5 fat marker. You're absolute brilliant if you can get this. So what I'm going to do is just zing over here. I need to teeth out that. Can I copy that, please, Bob? Yes. Let's go back over here, please, Jim. And we will, thank you, Sally. We will put that there. And now what we want to do is we're going to have a look. This was a 5 marker. This came up in whatever year it came up, but it came up on one of your exam papers. Determine the rate of reaction for 0.05 at 80 seconds. Now, that means we want to use this line, not this line. It's 5 fat marks. They want it to 2 sig fig, so even if you flop, but you correctly round, whatever calculation you make, you correctly round to 2 sig fig, hopefully to give you error carried forward. Now, here's the problem. What some people might do is we might just go, let's go to 80. 80 seconds is there. So they're testing, can you read the graph? Oh my good gosh. Ba-bum-ba-bum. What we want to do is zing that up there. Oh gosh. Oh my days. Now, let's see who can get the answer. I believe that's 80 seconds. Each one of these little cubes is worth 10. Let's see who can get the old answery. Oh my gosh. Dun, 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 dun. We're going to be moving on after this, so yeah. Okay, this is a little harder than you think. Don't have a ruler. Nice. Yeah, changing y over changing x. 0.63. Love it. Okay, here's the issue. If you did, I wanted to just give you a little bit of time for that. If you did 50 divided by 80, you're going to limit yourself to like 2-3 marks. Okay, so if you did this, you still get a couple. Where's my calculator? I can't be doing a lesson without my calculator. Where's my, what the, oh, here we go. Blind as a bat. So if you did this, you're going to limit yourself to 2 marks, guys. You get like this, 3 marks. I think they'll give you 3 marks if you round correctly. 0.625, and that will be centimetre cubed per second. What have I done wrong? Okay, let me get rid of Petro. You know, Petro is a little bit, you know, occasionally people you get one of these. Yeah, sorry guys, we get a little bit of a bell end like that. Thank you for putting him in a timeout. I'm gonna slap him in one as well. Yeah, you get a couple of them sometimes in the chat. So anyway, by the way, 0.625. If you did this and you round to 0.63 centimeter cube per second, great. That will get you. That should get you mins. That should get you mins of like 3 marks. However, what did they actually want you to do? They wanted you to do a tangent. So they wanted you to do this. When you have a curved line, you've got to do a tangent. Now, I'm going to be rubbish on this, but let me show you, because you might well get this in a rates of reaction question tomorrow. You're going to draw a tangent to the curve at the point. Now, I've missed that. Sorry about that, guys. So where that is, you should draw a line there, and it should be visually equal on either side. So I'm not going to be able to do it much better than that online, okay? If I was in real life, I could maneuver my ruler. But you get the idea. The examiner is going to give you a mark just saying, is there a space between this line going like that and that dot there? And if you've drawn this line going up from 80 to 50, he's going to give you 1 mark. If you've drawn that straight line, well, that's a bit crusty line that I've done, it's going to give you a 2nd mark. Now what you're going to do, you're going to make a triangle anywhere along this line. I would suggest easy numbers. Look, that's kind of easy down to there. And you're going to do, this is X, this is Y, and you're going to do your change in Y over your change in X. And that is going to give you your thing. So in my one, and my one's going to be wrong, it would be, what is that? That's 100. X is 100. So on mine, the change in X is 100. So if you have a look at my crusty little thing, change in X is 100. Now the examiner will use what you have drawn. So do not panic. 10, 20, 30. So mine is going to be like that. My change in Y is 30. So 30 divided by 100. And I'm going to get, like, I can definitely tell mine's wrong, because I got like 0.3, and it's not going to be 0.3, because why would they ask you to do 0.3 to 2 significant figures, right? They ain't going to do that. So anyway, I'm going to go centimeter cube per second, but it's very hard to do the tangent there like that. Anywho, yeah, they want you to do a tangent. So right, just thought I'd do that. We're going to move on. We're going to do equilibria now. So very quickly, I'm going to rinse through equilibria. Then we're going to do some questions. And then we have finished this section. And we're going to go on to the organic chemistry. And then we're going to do chemistry of the atmosphere. So I need to speed up a little. So let's go through Le Chatelier's principle. Oh, I can't spell this, dude. Oh, it's an E. Le Chatelier's principle. First of all, oh, sugar. I'm gonna write a reaction. Some of you, if you're triple, you know what this reaction's called. If you're sugar, you don't know what that reaction's called. So guys, this is known as the Haber process. I'm going to need 3 of them. Okay, this is known as the Haber process. We're going to do like 2 or 3 questions on Le Chatelier's principle now. So a couple of multiple choice and 2 written questions. So this is Le Chatelier's principle. And by the way, this is known as a reversible reaction. This symbol here is the reversible symbol. This symbol right there, that's known as the reversible symbol. Those reactions can go in both directions. They can reach something called a dynamic equilibrium. Now listen carefully. A dynamic equilibrium can only happen, so you need these conditions for EQ. I'm using EQ for equilibrium. It's got to be a closed system. Nothing must be able to get in or out. And it has to be a reversible reaction. If it's not a reversible reaction, it can't reach equilibrium. So it has to be a reaction that can go both ways. And it has to be a closed system. What is a closed system? A conical flask with a bung in the end. Okay, a beaker with a lid on. You get the idea. So we've got a closed system here, and Le Chatelier made a principle that basically, Le Chatelier's principle, so LCP, Le Chatelier's principle is this, and you've got to look at the language here. The EQ position will shift in the direction to oppose a change. So essentially, any change I make to this reaction, the reaction will shift in the opposite direction. But you've got to use the right language for GCSE. You can sit there for hours. It's too late for that, trying to understand it deeply. You just, when you get one of these, you want to talk about equilibrium position. Unless it asks about rate, I'll come on to that in a second. So let's whip through this, do the questions, and then move on. So what we're looking at is, this reaction is an actual exothermic reaction. I can't remember the numbers exactly, but it's like minus 93 kilojoules per mole. Whatever that means, it's exothermic. That means it releases heat. So I like to think of these reactions that release heat, they're actually losing energy. They're losing energy to the environment, but the environment gets hotter. You can't write this in your exam. You won't get marks for writing that. I like to think of exothermic reactions as hot reactions and endothermic reactions as cold reactions. So the moment I know, it will tell you in the question that this is exothermic, or if you're triple, it will give you the minus sign. So I know that that is exothermic, then this is the cold side. This is the endothermic side. So what Le Chatelier said is the reaction is like you guys, it's a moody teenager. So whatever your parent asks you to do, you do the opposite, right? Go to bed. No, I'm going to stay up. Whatever. That's what Le Chatelier's principle is. So if I start heating up this reaction, if I heat up this reaction and I increase the temperature, what's going to happen? If I increase temp, the reaction's going to say, I don't want to get hot. I'm going to the cold side. So if I increase the temp, the reaction goes to the cold side. Okay. Now in this reaction, the cold side's on the left. So you would say increase the temp. This is how you'd answer it. What would happen to the equilibrium if the temperature increased? You'd say the equilibrium shifts to the left. Now, if it was a 2 marker and you had to explain, you would say because it's an exothermic reaction. So you just point to the examiner. I know this is exothermic. So exothermic reactions always shift to the left when you heat them up. Now, if I decrease the temp, what would happen? If I try to make the reaction cold, which way will it shift? If I try to make the reaction cold, which way will this shift? I'm going to get onto organic chemistry next. If I try and make this reaction cold, which way will it shift? To the right. Thank you. Yes, to the right. Because it's a moody teenager. You're trying to make it cold. It goes, no, I'm going to make it hot. It does the opposite of what you do. So it's going to shift to the hot side. Now, you're not allowed to use the language hot side. It just helps me think temperature does the opposite, right? But really, your answer would be shift. The equilibrium shifts to the right because it's an exothermic reaction. You just point out what the reaction is. Now, we're just going to deal with pressure and then we're going to move on off of this and I'm going to give you the questions. So we're now going to look at pressure. Pressure is easier. Temp's the hardest bit there to explain. That's difficult. That's level 8, 9 stuff. So you can still get a level 8 or 9 and get that wrong. So don't over panic. Here's a couple of things to just go through with you. Pressure. So if I increase the pressure, if you increase the pressure of a reversible reaction, it will shift to the side. When you increase the pressure, the particles start smashing into each other more. So the reaction, moody teenager syndrome, Le Chatelier's principle, says, no, we're not going to bang into each other as much. We're going to slow down. We're going to go to the side with the least gas molecules. So if you increase the pressure, the reaction will shift to the side with the least gas molecules. So if I increase the pressure, which way will this reaction shift? Well, let's add up the gas molecules. 1 nitrogen, I've got 1 NN, but I've got three. I've got HH, HH, and HH. I've got 4 particles here. You might say, but sir, haven't you got 6 here? No, I've got 2 particles because these are all joined together. This is one ammonia particle, and then there's a second ammonia particle. So there's less gas molecules on the right. In fact, there's 4G over here and 2G here. So increasing the pressure shifts EQ to the right. And what you need to say is, as there is less moles on right. You can say moles, you can say molecules, either one. Is everyone cool with that? Yes, yes, yes. Excellent. This does come up. By the way, this is combined as well. So before people go, this isn't combined. It is. Triple do a Haber process, and you have to know about compromised conditions and ion catalysts and stuff. By the way, a couple more things on equilibrium, and then we're going to do the questions, and then we're done with equilibrium. Couple more things on the EQ, peoples. This is one of the biggest topics, by the way. Some of the other topics are a lot shorter than this one that we've done. We've just done rates and EQ. It's taken an hour, but not an hour. It's taken about 50 minutes, but the other topics are shorter than this. Organic chemistry is mafusive if I do all the triple stuff, but I'm going to start with the basics, and then I might come to the triple stuff after for the organics, because otherwise it's like a dead period of 20 minutes for people. So chemistry in the atmosphere is the same for everybody pretty much, so we're going to go through that as well. Right, what was I going to say? Yeah, you do need to know, how does a catalyst, there's 2 questions. They love this. This is absolutely up AQA, EdXL, OCR street. They absolutely love it. Love, love, love this question. So watch this question. These are 2 different questions, all right? So watch out for these. I'm going to say, how does a catalyst affect EQ? How does a catalyst affect the equilibria? I'm going to go through that as well. Yes, they speed up reaction, but check what I didn't ask about the reaction. I said, how does a catalyst affect the equilibrium? It doesn't. It does not. It doesn't change the equilibrium. It just speeds up the rate of reaction. So watch out though, because now you know that catalyst doesn't affect equilibrium. What these sneaky little bums from AQA do, these nasty little people, they give you an equilibrium question. They ask you about the equilibrium position. You think you're done with rates. We're not doing rates here. And then right in the middle of an equilibrium question, in just one of them little B part 3, they say, how does the catalyst affect the rate of reaction? Affect rate. And if you've been a good student, you've memorized that catalysts do not change the equilibrium, but these sneaky gits, and you write, catalysts do not change equilibrium. That's not what they asked. This time they asked, how does a catalyst affect rate? And you say, oh, catalyst increases rate. So watch out, because they'll try to trap on you, and they'll do it in the middle of an equilibrium question. They'll switch to a rate question. They could do that with temperature as well. How does the temperature affect the rate? And you're in the middle of talking about pressure and shifting the equilibrium. Watch out. Okay, let's bust a couple of questions. Oh my God. Oh, what's it? Lion getting excited? Yeah, I haven't had a look. Right, the problem is I get so the gases. Right, check this one. Gases, nitrogen dioxide and nitrogen tetroxide reach dynamic equilibrium in a sealed container. The equation for the reaction is 2. Just for those of you that can't see, I'm going to write the reaction here a little bit bigger, because I know some of you like it like that. So there we go. And we're going to go like that. And then we're going to go N2O4G. The forward reaction is exothermic. Listen, I like to write this. As soon as they tell me that, I'm like, oh. They've told me that the forward reaction is exothermic. So that's hot. That's cold. That's going to help me. What happens to the position if the temperature is increased? Which way does it shift? Which way does it shift? Yes, it's going to shift to the left. And the reason it's going to shift to the left, because it's a moody teenager, it always does the opposite. So once you write hot and cold, if you know it's exothermic, that tells you that it's a hot reaction. You're not allowed to call it a hot reaction, but that means it's going to shift to the opposite. Now, if I had said, what happens if they increase the pressure, which way would it shift? What about if we increase the pressure? Which way would it shift if I increase the pressure? I'll give you a boom if you can get that right. Which way would it shift if I increase the pressure? So, if I increase the pressure, it will shift right. Well done. Boom. Yes, I'll give you a boom. Yeah, for those people who said to the right, you get the boom. Well done. Boom. Well done, well done, well done, well done. All right. Let's move on. Let's go to this one. Hydrochloric acid added to an aqueous solution. This is a little bit more tricky. Copper compound A plus hydrochloric acid goes to copper compound B plus water. Right. Okay. The reaction mixture is green when both copper compounds are present. How can the equilibrium position be shifted to make the reaction mixture more yellow? Well, that means we want to shift to the right. Have they told us anything about it? Add more hydrochloric acid. Remember, it's moody teenager, people. Add more water. Leave the reaction mixture for 30 minutes. What do you reckon? Excellent, Lucy. Add more hydrochloric acid. Excellent. Add more hydrochloric acid. If you add more hydrochloric acid, it's a moody teenager. It's going to say, oi, I don't want that. I'm going to move over here to break the hydrochloric acid down. So it will shift to the right. Super. And that is the one we want to do. Right, I'm just going to give you one. I was going to do two. I'm just going to do one written question on this. Then enough of this business, because you guys seem to be all over it. So what we're going to do, let me give you an EQ question, and then we're going to move on to organic chem. All right, let's go. What am I doing? Where's my rates of reaction? I wrote down exactly which one I wanted. No, EQ. Oh my gosh. Oh my good gosh. All right, let's do that one. Hold on, I don't want it to be too bad. I want it to just be a little... We want to move on. Come on, don't make it a big, no, that's not what we want. Blimey, O'Reilly. All right, here we go. I will address the chat, and I will be booting out people that are spamming. If you're spamming up the chat, you will be getting booted out. You'll be getting a 30-minute ban. So don't be spamming up the chat, because you're going to get a 30-minute ban, because we're all trying to revise here for the exams. So yeah, what are we doing? All right, what I'm doing is smashing on this question. So it's going to go a little bit black, and then it will be back. Okay. Oh my gosh. OMG. I don't really need to repeat that. I don't know why I did that. There's like 4 parts to this question, so you can see. And before people cry about it, this one's from a combined paper. So I know some people say, this isn't for me because I'm combined. No, this is for you. This is from a combined paper. So, which is good, because some of the TRIPS people, you've done all the TRIPS papers, but you might not have done all of the combined. So there we go. Right, last bit. Okay, let's just do that one and lick that one there. Oh my gosh, that's too much. OMG, I'm gonna have to move that up. Oh my gosh. All right, I'm going to go through this one for you guys, and then we're done with equilibrium, never to be looked at ever again, unless you're taking A-level chemistry. Then you're doomed. Boy, poor Ishal, she's having to like work hard to boot out all these wallies. Okay, ammonia is produced when a mixture of nitrogen and hydrogen reacts. The equation for the reaction is N2 plus 3H2 goes to 2NH. So once again, it's that one. Okay, so nitrogen is obtained from the air. The mixture of nitrogen and hydrogen must contain carbon dioxide and oxygen. Explain how a sample can be tested to show that carbon dioxide is not present in the mixture. How do we test carbon dioxide? Excellent. Bubble through lime water, it will go cloudy. Right, yeah, so if you put lime water, it won't go cloudy, yeah. Or you could just say if CO2 is present, it will go cloudy with lime water. You're right. Or you can argue it won't go cloudy if there's no CO2. You get the idea. Right, a catalyst is used. Explain, check the reading here. How does a catalyst increase the rate of reaction? So we might already think we're doing equilibria because we've seen that sign, but it's rate of reaction. How does a catalyst affect the rate of reaction? So we want to say lowers activation energy, right? It lowers the activation energy. We can also say provides alternative route or pathway. Some people like to do that. Okay. Okay. It did say increases. Sometimes it will say explain how the catalyst affects the rate of reaction. Then you get 1 mark for saying increases the rate. Okay. What about up here? Explain how an equilibrium is reached. What do we need? Do you remember what the factors were to reach equilibrium? Equilibrium is when the forward and backward reactions happen at the same rate. Very good. But how is it... When it says how is it reached, I'd be tempted here to bust out a little... some extras on that. I'd be tempted to go... I'd be tempted to sort of talk about how it's actually reached. How can we make it get there? Like... What do we need to say? Closed system. Thank you. So we need a closed system. I would put reversible. We need a reversible reaction and a closed system. And guess what? I'm going to put what you guys said as well. And then I'll put the definition, define. I'm not going to write it because you've done it in the chat. Define EQ. And then you're going to say the forward and backward reactions happen at the same rate. Suggest how a catalyst. Now look, check the difference. How does the catalyst affect the EQ position? Right, it doesn't affect it, but you can say it doesn't affect it. You can say it reaches equilibrium faster. It will reach equilibrium faster. Why doesn't it change the position? Here is the second mark. This is a hard one I didn't go over with you guys. Catalysts increase the rate of both forward and backward reaction equally. That's why the equilibrium position doesn't change. The catalyst works on both directions, so forward and backwards rates equally. Yeah, so it increases both rates by the same amount. Right, what is the effect of increasing the pressure on this reaction? What happens if we increase the pressure? Now notice they haven't talked about equilibrium position. They've used this word yield. Yield is always the right hand side. So if they say the yield increases, they mean it shifts to the right. Yield increasing is the same as shift to the right. Yield decreasing is like saying shift to the left. So watch out for that as well. So what do we want to say? Does the yield increase? It shifts to the right and that will increase the yield. Absolutely. Why does it shift to the right? Because we got 4G, 2G. If you increase the pressure, it will say, I'm not doing it. And it will shift to the right. Excellente. Lovely jubbly. And then, of course, we could tell you the reaction's exothermic. How will the increase in temperature affect the equilibrium? And it would shift to the left to the endothermic side. Okay, right. Let's get off of this topic. I think the next topic is... Oh my God, it's organic chem. I'm just going to get straight in with the questions rather than teach you about the basics of organic. We're going to go straight in with some questiones. Okay, let me hit you with a few multiple choices on organic chemistry on the hydrocarbons. So let's go. Yeah, let's have a little warm up on hydrocarbons.
Here we go. What?
Okay, you can have a boom if you can get these two right. Anyone who can get these two right? So, tell me the box you would tick. So, first one, petrol contains many alkanes. Which of the following compounds is an alkane? C2, for those of you with, like me, with visual difficulties, I'm giving you the enlarged version. Yeah. So, which one of them is an alkane? Which box? Which box? Third one. Who said third one first? Yep. XI, XZZ. Yeah, I can't read, but you get the idea. You're getting a boom. Well done. Boom. Okay, hydrocarbon molecules containing 7 and 8 carbon atoms can be produced when heavy fuel oil is processed. Which pair of hydrocarbon molecules would both turn bromine water colourless? Ooh, who knows? You're going with one. Okay, you're absolutely right. Does anyone know? I'm going to give you guys a boom for that as well. Can anyone explain why it's one? Can anyone explain why it's one and not one of the others? Why is it one? Why is it one? You're absolutely right. Boom. Don't worry, I'm not going to do that every time. Right, yeah, you're absolutely... Holy pacholi, what happened there? Yeah, you're absolutely right. They're both alkenes, okay? And if they're alkenes, these are alkenes. They have the general formula CnH2n, and this means they contain a double bond. These bad boys, well, this bad boy, and this bad boy are all alkanes. Alkanes, you have to know this off by heart, whether you're triple or whether you are combined, have the general formula CnH2n plus 2. So you double the number of carbons to get the hydrogen, and you add 2, which is the 2 hydrogens at the ends. So remember, like if you had ethane, it has 2 carbons. That means it has 6 hydrogens. So you go 2 times 2 is 4. Add 2 is 6. So you know the formula is C2H6. Whereas the alkene version of that is known as ethene. And ethene is an alkene, so it just has the general formula like that. The hydrogens are always double the number of carbons. Anywho, you can combust both of these. You can burn both of these, remember. And combustion reactions, it's almost... pretty sure you might get a combustion reaction. So just make sure, I'm going to go through one with you now. Just make sure for combustion, you know how to balance this. So for example, if you had CH4, which is methane, plus oxygen, what 2 things do you always make with combustion? By the way, combustion's always exothermic, talking about OMG. So we're always going to make carbon dioxide and water. That is right. Carbon dioxide plus H2O. Now, how do you balance them? These, if you're crap at balancing and you're one of those people who's like, balancing, these are the easiest to balance. Just see how many carbons you've got, and that's how many carbon dioxides you need. So if there's 1 carbon, you leave the carbon dioxide as 1. 4 hydrogens, slightly different. You're going to divide that by 2, and you're going to put that number in front there. So you go H divided by 2 is 2, bish bash bosh. Now what the last thing you balance is the oxygen. I've got 2 oxygens there. The big 2 is 2 times O, so I'm going to put a 2 there, and we're balanced. Let me give you another one and see who can come up with the correct numbers for this one. All right, who can balance the combustion of ethane? What two numbers will I need to balance, or what three numbers to balance the combustion of ethane? So what we're going to do, we're going to see the 2. Have a look. It says 2, so you're going to put a big fat 2 there. Then you're going to see the 6. You divide by 2, and you put a big fat 3 there. And that is most of your balancing done. The final thing you balance in a combustion reaction is always the oxygen. So you're going to go 2 times 2. There's 4 oxygens over here. And we're going to go 3 times 1 is 3 oxygens there. And then we're going to panic and go, oh my God. Oh my God. What do I? Just put 3.5. Only in combustion reactions you are allowed to use fractions. So you could put 3.5. In organic chemistry, in combustion, you can use fractions, so you can put 3.5. All right, just thought I'd run through that with you. Of course, if you don't like that, you can times it all by 2, but who would want to do that? Just use the fraction. Right, got a couple more of these, and then we're going to do a long form question on this. So, by the way, guys, don't forget to hit the like. Make sure we hit the like, people, and have a go at these ones. Oh my days, what am I doing? What am I doing? What am I doing? OMG. Yep. So what we got, guys, going down, let's have a little look. Cracking breaks down the large hydrocarbon molecules into smaller hydrocarbon molecules. Which hydrocarbon molecule when you crack to produce that? So if we're producing C8H18, it's coming from something. So it's got to be bigger than C8H18. So it can't be that one. That's smaller. It can't be that one. And it can't be that one. So it has to be the last one. And hopefully you could work out what the other one would be. Look, what would the missing one be? So if it was snapped, with cracking, you crack a big hydrocarbon into smaller, more useful hydrocarbons. For instance, C8H18 is octane, and that's very useful in petrol. That's what you fill up if you're still driving a petrol car. And of course we've got C4 left over, and we've got 8. Now notice that is CnH2n. This is an alkane, but smaller and more useful, and this is an alkene. Cracking always makes small useful alkanes great as fuels, and alkenes that we can turn into plastics by addition polymerization. So cracking's a very useful thing. What type of compound is octane? Alcohol, alkane, carboxylic acid, ester. Hopefully you all know that. That is an alkane. Now, do you know the conditions for cracking? Does anyone know what conditions you need for cracking? In order to break a big hydrocarbon, what conditions do you need? High temp and a catalyst. Boom! Does anyone know the actual name of the catalyst? Who knows the catalyst? Zeolite will do. But you can use aluminium oxide. Aluminium oxide or zeolite. Good. You have steam cracking, or you have catalytic cracking that uses catalysts. So catalytic cracking uses catalysts, and steam cracking doesn't use a catalyst. So there we go. Right, what are we going to do? What are we going to do? Two more of these, then I'm doing a long form one on this. We'll do a fractional okay, alkene needed to make polypropene is produced from crude oil. So the alkene needed to make polypropene is produced from crude oil. Which two processes are used to produce the alkene from crude oil? Excellent. We're going to need fractional distillation followed by cracking. So, and by the way, a bonus point, anyone that can tell me what type of reaction, oh my God, what type of reaction is cracking? Is it oxidation? Is it combustion? Is it... Hey! THESP 52! It is not either of those. THESP 52 has got it in one, it's thermal decomposition. Well done. It's thermal decomposition. What type of bond joins the atoms in a molecule? They're going to be covalent bonds, but between the layers will be cross links. Now, if you've got covalent, but if you've just got weak intermolecular forces, you'll melt easy as in a thermo softening plastic. But if you've got covalent bonds between the molecules joining the chains together, then you're going to be a thermosetting. Right, I'm going to give you a long form question because this is a big chapter, so I'm going to give you a long form question on this. Let's go. We want a hydro. Let's do a fractional distillation. Fractional distillation. Yeah, let's do one of these. All right, mate. Get over there. See if you guys can do this. Do 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 do. All right, I'm just screen grabbing. So when I screen grab, it goes a bit dark there, and then so bear with me for the next 20 seconds while I screen grab up some bits. Now, splish, sploosh, splash. Okay. Let's see if you can do these ones. Oh my gosh, what am I doing? Come on, see, sort it out, mate. Oh no, 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 no. Okay, let's have a look at these little questions. I know I said it's long form. This is like more short form. Right, crude oil. Now, this is a 4 marker, so I'm going to run through this with you, okay? Because this is a 1 marker, but I'm going to take the chance to go through what would be a 4 mark answer. If you're asked, how does it happen? So if you don't know how fractional distillation happens, it's how we split crude oil into the... It's a physical process, right? It's a separating mixtures, fractional distillation. So it's... You're not doing a chemical reaction in here. It's a physical process with boiling, evaporating, sorry, and condensing. They're 2 of your key words. So what we're going to do for number... Yeah, I'll start here. Number 1, you're going to... You can say heat or evaporate or vaporize crude oil. So if I'm asked how to answer how is crude oil separated, this is what I'm going with. Number 2... fractions rise up the tower. I can say hydrocarbons here. Fractions rise up tower because I've just said we vaporize them. And then what I want to do is in fact, I just need to rub that. I'm going to go with this. So I'm just doing it in 4 marks. The tower... Oh, I'm running out of room. Has a temp... gradient. Okay, what the hell is that? The tower has a temperature gradient. All I'm trying to tell you is the tower is hot at the bottom, cold at the top, and you can tell the examiner in those words. I could have just used those words, but I'm stupid, so there we go. I said temperature gradient. Oh, I can't get the cold over there, right? So all we need to tell the examiner is we vaporize the crude oil. It starts floating up the tower, rising up the tower. The tower has 2 different temperatures. It's hotter at the bottom, it's colder at the top. You can call that a temperature gradient. And then for my 4th mark, I'm going to get 2 keywords in here. I want to say different fractions condense. Oh, I haven't got the room. I haven't got the room. Different fractions condense at different parts of the tower. Okay? Based on their boiling point. So that's 2 marks. So you want to say vaporize, 1 mark. Rise up the tower has a temperature gradient, 2, possibly 3 marks. And then for the last 2 marks, we want to say different fractions condense at different points of the tower based upon their boiling points. Excellente. Yeah, you kind of got to know the order because the way they word this sometimes is like this. So, and it's different in different specs, all right? So, yeah, you've got like heavy fuel oil, then you've got like, what is next? I can't even remember. Diesel, kerosene, petrol. They've put naphtha in there sometimes. I'd have to have a look. In fact, I've got it here. Yeah, you guys are heavy fuel oil, diesel, kerosene, petrol. There's an extra one here, so for some reason, there's an extra one. And then at the top is refinery gases or liquid petroleum, LPG. You know, in America they say step on a gas, liquid petroleum, that's LPG. Yeah. Right. Crude oil vaporizes, goes up the tower. Each fraction, what we want to say is condenses. That was supposed to be my point 4 at a different level. Why do the fractions separate? They have different boiling points. Okay, so in my explanation, it should have been vaporize, rise up the tower. The tower is hot at the bottom, cold at the top, and the fractions condense at different points because they have different boiling points. So my keywords are vaporize, temperature gradient, condense, boiling points. They would be my 4 bullet points I need to remember. What would the name of this alkane be? Anyone got the name of that alkane? Propane. Cheese. Very good. Boom. Right, let me give you the rest of this and then we can move on. Move on. Oh my days. I'm going to give you the rest of this question. Okay, methane is an alkane. What is the general formula of alkanes? I will come back to organic chemistry a bit later, by the way, guys. I'm just going to, like, the triple is, the combined is kind of nice and easy. So I'm just going to go through the combined bit of it first. By the way, somebody asked me, how is coal formed or crude oil formed or coal formation? Or you do need to know that crude oil comes from the decomposition. That means the decay of marine, which means the sea, organisms. So you can just say organisms from the ocean decayed, formed crude oil. Now, coal actually came from plants. Crude oil, which is the thick black liquid that we drill out the ground or from under the seabed, is from sea creatures, sea organisms, which we call marine organisms. So from the decay of marine organisms over millions of years under heat and pressure. So the heat and the pressure decayed these over millions of years to create crude oil. Like some of the conditions were quite unique, like anaerobic and things like that. Now, what is the general formula for alkanes? So hopefully you all got that right. Balance the equation for doing methane. We just did this one. So look, they might put that there, sneaky little gits. We only actually need 1 there, so we don't need to put anything there. We've got 4 there, so we just put a 2 there, and we just put a 2 there, and it's bish bash bosh. It's all balanced. So they're sneaky. They left you with these. You didn't need to put anything there or there. Look, if you really want, you could put a 1 and they're not going to take marks off for you putting a 1 there. Ethene is an alkene. Which reagent tests for alkenes? Anyone get it? Plankton, absolutely. If you like SpongeBob. No, plankton absolutely is the marine organism that most crude oil is made from, but it was like an ancient form of plankton millions of years ago. Bromine water, well done. And do you know the colour change? Who knows the colour change? What's the colour change for bromine water? Yeah, you guys are all over that. Anyone know the colour change? Decolorizes. Yeah, actually, yeah, decolorizes. It's orange originally and it goes colourless. You can say it decolorizes. Well done. Yeah, good. Okay, we're nearly there. I think I should just do one little more and then oh, I'm not doing that. Fudge that. One second, peoples. Oh my good gosh. Where are you? Oh my god. I didn't go through that. Okay, we didn't go through that, did we? No. What's wrong with me? Absolute bonks. Bonkaroony. Okay. Alright, mate. Sorry, talking to myself as I'm Locating, 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 locating. Let's go. I'm so tired. Okay, guys, let me give you this one because this is just going to test you. If you're in, if you're combined, this is like very common for you, and triple you need to know, obviously. So give me the 3 markers. What are the 3 points? I just waffled about that, and I waffled about this. I gave you the 4 of this as well. So what are the 3? What are the 4? What you got? How's crude oil formed? This is from 2021, I think. And then I think I'm going to go on to evolution of the atmosphere for a little bit. We're going to do evolution of the atmosphere, but I might go and make myself a coffee first, and then we're going to do evo of the atmosphere. Oh my gosh, what have I done there? You absolute chieftain. Get that up, put that there, do that there, flip the script, bish bash. Okay, so what we got going on, I'll put the rest of the question up in a second. Let's deal with this first. So hopefully you've put the answers right. So describe how crude oil is formed. Yes, so we want something like dead marine organisms. Yes, you can say plankton. Yes, you can say creatures in the sea, animals in the sea, life in the sea, organisms in the sea. Yes, you can say all of those. So dead marine organisms. It's going to get me a mark. And then decayed, I want to put that over millions of years. So we need to say millions, not just a few hundred years or thousands. It's got to be millions of years. And then we say under heat and pressure. I will check the mark scheme. I reckon I got 3 marks there. What do you reckon, guys? Let's hope so. I got the mark scheme. Hold on. What the? I hope that's a boom. We'll have a look at one of those questions on copper sulfate. I'm getting to that. I'm getting to that, peoples, with the potables water and the sewage water. I'll get there in about 4 years. So if you're still on the live in 4 years' time, we'll cover that. Look, there you go, guys. You didn't even have to say heat and pressure. Scumbags. You just had to say plankton, allow marine animals, organisms. Brackets, marine means in the sea, but they're basically any animals. So animals decayed. Compressed under mud. That's basically pressure and heat. Over a long period of time, millions of years. They should accept heat and pressure for compression. Compression and pressure are the same thing. So allow compressed. They like buried in mud. Yes. Describe how crude oil separated into fractions. What were our 4 marks? So this is what I believe. I'm going to put the mark scheme up. I believe it's going to be vaporization. And then OMG, tower has temp gradient. We might have to say rise up tower. Fractions rise up the tower. Don't talk like an idiot like me. And then condense at different heights, points of the tower, dependent on their BPT. That means their boiling point. That's what I'm going for 4. I hope I get 4. Otherwise, I'm not going to pass my GCSE. And then I'm going to cry. Oh my good gosh. There you go. There we go. Crude oil heated. You can allow vaporization, boil. Okay, I said vaporize. I think it's a better word. Or evaporate. So evaporate, heated, vapor. You get the idea. We're in there. Fractions have different boiling points. Fractions collect at different at different levels. Collect, it should be condense. Oh, there's condense. Yeah, vapors condense. Okay, cool. So condense, heat, fractions have different boiling points. Collect at different levels dependent on their boiling points. Okay. Vaporize means the same as evaporate. All right, one more part to this question, and then we're done. I promise with this, and we will move on. We're going to look at evolution of the atmosphere, but first of all, I've just got one more part to this question, and then we're going to look at evolution of the atmosphere. So, what is the general formula for alkanes? And explain the trend in the boiling points. I need to give you the table, otherwise how can you explain the trend? Oh, and I do need to tell you something else about the hydrocarbons, although tell you probably already know. OMG, go away, and back there, and here we go, lickety split. Ah! Glasses down. Yeah, we're going to do potable water. We're going to do formulations. Yep. Of course, there are loads and loads of listen. There are plenty of other YouTubes you can go on. I recommend some of the other YouTubers as well. They're gonna take you through all the content as well. What is the general formula? CnH2n plus 2. Here, explain the trend, guys. What is the trend? Explain that trend. Why do alkanes increase as their size increases? So why, as they get bigger, do they increase? Why do they get bigger? I will be doing triple. We will be doing all the trips. Bro, I don't blame you. Yeah, as soon as 8:30, jump over to... Listen, there are plenty of other people. You know, there's plenty of other channels. Yes, brothers and sisters, welcome to exam.com. Now there's 32 seconds left before the last exam of this exam season. I know what you're thinking. Is it too late to invest in our incredible slides which cover all of the content? Of course it's not too late, man. There's 29 seconds left before the final exam, and just for 999.99999 you can get our incredible PowerPoint slides. Just check out the quality of these slides. Look at them. All right, now I know what you're thinking. Am I doing this just for the money? Well, I'm not. This is to help you, because I want to help you. Yeah, that's what we're here for. For just 999.999. I know what you're thinking. We're now 2 minutes into the last exam. Oh my gosh, is it too late to get this? No. Put your hand up. Ask the invigilator if you can go for a wee. Pull out your phone and just get these slides right now. Oh, and by the way, if we get 50,000 likes tonight, then Mo's going to get his abs out. Yeah, sorry, I can't help being a bellend. It's just in my nature. As these molecules get bigger, so we get increase, as they increase in size, the intermolecular forces increase, right? So IMF, intermolecular forces, increase, more energy to break, so higher boiling points. All right. We're going on to evolution chemistry of the atmosphere, but I need to go and make myself a coffee, folks. So, yeah. It's time for a coffee feat. Hold on, let's get to chemistry in the atmosphere. That's not chemistry in the atmosphere. What's that? Chromatography. Ooh, no, thank you. What do people want to do next? We can do chromatography, chemistry of the atmosphere. I'm not doing fertilizers yet because they're going to make me pass out. Triple organic. No, we don't want to do condensation and all of that. Where's chemistry of the atmosphere? Oh, my days. I've got to bust out a coffee, people. Otherwise, I'll pass out. Life cycle assessments, absolutement. We can do all of that. Here we go. We're going to do a bit of chemistry of the atmosphere next. It's nice and easy peasy, lemon squeezy. I promise not to take 18.6742.9 million hours over it, which will happen. So, yeah. Let's do just a couple on chemistry of the atmosphere. It's nice and easy. By the way, it's ripe for 6 markers, chemistry of the atmosphere. I'm going to go and bust out my coffee right now. So see if you can do these, guys. And in fact, I'll leave you. I'm not going to go get my coffee yet. I'm going to get my coffee after I put on a 6 marker. Okay, so I'm going to put on a 6 marker. All right, anyway, this question is about greenhouse gases and climate change. Carbon dioxide and methane. You need to know these are both greenhouse gases. Which of the following is also a greenhouse gas? Probably surprisingly, water. So in AQA, you have to know methane, carbon dioxide and H2O are all greenhouse gases that cause global warming. Which 2 gases are produced when fuels burn in car engines? So we're going to get carbon dioxide always given off. And we don't get ammonia. And we don't get nitrogen or oxygen. We get carbon monoxide. Carbon monoxide is formed from something called incomplete combustion. And I just want to clear one thing up. It's poisonous. But here is what I want to clear up. It's part of evolution of the chemistry of the atmosphere. Is just be aware, a lot of students lose a mark because they label CO2 as a baddie. Right? CO2 is dangerous for the environment or bad for the environment, but it ain't that bad for you because you're breathing it out every day. So, you know, if CO2 is that bad, as you breathe it out, you'd be dying, right? So CO2 is not bad. We produce it in our bodies, okay? It's not a pollution. These are the pollution gases. I should call them pollutants, but I can't speak because I'm a bit of a spat. Pollution gases are nitrogen dioxide, sulfur dioxide and carbon monoxide. They're the ones you have to know. Oh, and particulates, which are like soot. Okay, so you've also got to know like soot. Anyway, let's do a nice fat 6 marker on evolution of the atmosphere and see if you guys can do evolution of the atmosphere. Oh my gosh. Oh my days. It's the World Cup, isn't it? Mexico are playing. Who are Mexico playing today? Is it South Africa? Or is it South? Are they in the same group as South Korea? That's going to confuse me. What they ask? I've written down evolution of the atmosphere, chemistry of the atmosphere. Let's do a 6 marker. All right. Hold on. Is that norms? Yeah, that's norms. So we need to just do. Where's 2018? Is that it? Yeah, that's it. And it's 6. Go. Da, 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 da. No. Huh? What the? All right. Oh my days. I think I've gone completely bonkers. Yeah, I definitely have. That's why I need that coffee. Right. Let's rewind. That is the question we want to do. I'm having a meltdown here. What? Okay, let me give you this. I'm going to give you a 6 marker. I need a Kofifi. So I'm going to go get a Kofifi. And yeah, see if you can do that one. By the way, this has come up like 3 times as a 6 marker. The evolution of the atmosphere. Explain how the percentages of nitrogen, oxygen and carbon dioxide in the Earth's atmosphere have changed from the Earth's early atmosphere. And then I'll go through the atmosphere and what you got to know. And I'll be back in 2 minutes. I will do phytomining. Oh my gosh, it's Sunster. Watch out, people. Watch out. Sunster's in the chat. Yep. Sunster's in the chat. Sunster's in the chat. Watch out, people. Watch out. Watch out. Watch out. All right. I'm getting my coffee. All right, all right, all right, all right, all right. So, listen, let me talk you through what's going down with the atmosphere. So, you got this question here. Well done. Yeah. So, essentially, I'm just going to generally talk through all your 6 markers on this. There's quite a few 6 markers have come up. Maybe this has come up 3 or 4 times. So it is a possibility. Explain how because most of this topic is about this. So explain how percentages of nitrogen, oxygen, carbon dioxide in the Earth's atmosphere have changed from the Earth's early atmosphere. So when the Earth was first formed, these are supposed to be incredible artwork. Check out these volcanoes. The Earth had volcanoes on it, and out of those volcanoes popped carbon dioxide, ammonia, which has the formula NH3, also was methane, and we've got various other bits and bobs coming out of the Earth's early atmosphere, but they're mainly focused on methane. You got some water vapor. Obviously we have to put water vapor, that is essential. There may have been some sulfur dioxide and some other things that come out of volcanoes nowadays. So how do we know that? Well, no one was around then, so just remember, no one was alive to know that. But looking at what volcanoes give out today and looking at planets when they first formed, they're covered in volcanoes. This is what we suspect was coming out of it. And so the theory is that over millions of years the Earth got colder. So like Earth was hot, and these were the early gases. These are the early gases. So you would just write down, these are the early gases. They came from volcanic or volcanoes. So you want to say released these gases. Now, so you would just name them. You'd say, oh, water vapor, methane, ammonia, CO2. You can use the formulas if you want. Then what we want to say is, over time, as the Earth cooled, CO2, H2O condensed. So water condensed. What did it form? It formed the oceans and the rivers and the seas. Okay, oceans, rivers and seas. So the H2O in the atmosphere went down first. The water vapor went down first because it became water. It condensed into liquid water. Now the thing about carbon dioxide is it's soluble. So some of the carbon dioxide dissolved in water. And guess what that formed? It ended up, I mean, it's a lot longer than this. This is the very basic version, but formed carbonate rocks. Things like limestone, like the White Cliffs of Dover in the UK. It formed chalk. It formed various carbonates, sandstone, all of that business. Carbon dioxide went in that. Carbon dioxide also eventually ended up in the bones of animals and the shells of sea creatures. But that's kind of jumping the gun, but I'm going to write it here anyway because I'm on carbon dioxide. Carbon dioxide was... oh gosh, what do I want to say? Converted, stored, incorporated. That's a serious word. We don't really want to write incorporated. So let's say stored in bones and shells of animals. So carbon dioxide was absolutely huge amounts in the atmosphere. Absolutely huge amounts, but it ended up dissolving in the water. It's right there now. It's dissolved in all of our oceans, and it's in the bones of every creature. Every animal on the earth has it in their bones or has carbon locked into their shells. Okay, so there we go. That's carbon dioxide dealt with. Now we need to talk about, well, what happened to nitrogen? Well, we know that nitrogen is used in the nitrogen cycle, and nitrogen's released into the atmosphere when things decay by nitrogen denitrifying bacteria, but I don't think you've got to know too much about that. So percentages of nitrogen, oxygen and carbon dioxide in the Earth's atmosphere have changed from the Earth's early atmosphere. So there wasn't any nitrogen in the air back then, but ammonia, what we can say, should we talk about anything else? Maybe we need to talk about the nitrogen. So in the early atmosphere there was no nitrogen, but we can say ammonia became part of nitrogen cycle. So what happened to the ammonia? Became part of the nitrogen cycle. Nitrogen gas released into air. So why did it become part of the nitrogen cycle? If I want, I can talk about nitrogen being in amino acids and proteins, but I think that's a little bit going extra. And then also what I did miss out is CO2. See, my order is not very good. CO2 used by plants in photosynthesis. So I'm just trying to get down everything that's happened to the carbon dioxide. Oxygen given out by photosynthesis. So CO2 was used in photosynthesis, and guess what? I could say to make glucose, but really it's to make complex organic molecules: glucose, carbohydrate, protein, starch. And the oxygen was given out by the plants into the atmosphere. Okay, and now what we want to do is, someone put in the chat, we could tell the examiner that we know that it's roughly 78% nitrogen, 21% oxygen in nowadays, and we got 0.04% CO2. So you can see CO2 is actually very, very small, but it has gone up 25%. So it was 0.03 about 200 years ago. So why people talk about carbon dioxide going up is because it's gone up from 0.03 to 0.04 over about 100 years. That's a 25% increase. So people are like, woo. But remember, when the earth was formed, it would have been like 50% carbon dioxide up there. It was a lot of carbon dioxide, because all of that carbon is locked into every animal and every plant. So that, imagine that carbon was in the air, and now it's in every animal, every plant. It's in rocks like carbonates, and it's in the bones of animals. Anywho, that peeps can take that. Yeah, there we go. Okay, what are we going to do? Let's have a little look at a couple of these. These are about pollution, and in cars. Oh, we haven't done analysis either. I've got to do chemical analysis as well. Which one is chemical analysis? Purity and chemical analysis. Yeah, we'll do that as well. Okay, guys. Got some atmospheric pollution. So, vehicles produce more atmospheric pollution in cities. How could atmospheric pollution in cities be reduced? So, nice and easy. Develop fuel-efficient engines. Use electric cars. What reacted with the limestone to cause erosion? What reacts with limestone? Remember, this is a carbonate. You might remember this from chemistry paper 1. What reacts with carbonates to form carbon dioxide, salt, and water? It's going to be acids, so acid rain. Let's look at a few more of these ones. These are to do with gases in our atmosphere. See if you can do these ones. Mexico winning. Lovely jubbly. I had Mexico down for a win.
Stick around.
I'm gonna have to science the shit out of this.
Yep. What we're going to go here. Carbon dioxide is produced in the reaction between hydrochloric acid and calcium carbonate. Which one tests for carbon dioxide? You know the coup. It is lime water turns milky. Now, part of the chemical analysis, if you're doing combined science and you're doing triple science, you have to know these ones. So who can tell me, before we answer these two questions, or I go through these, what is the burning splint popping? What gas is that for? So, this is hydrogen gas. This is not for triple. Everybody needs to know this. A glowing splint relights. This is for oxygen gas. And damp litmus paper that gets bleached is testing for ammonium ions or ammonia gas. You can say it's the test for the gas ammonia or ammonium ions. So, nice. Now, what's happening there? Sugar Ray Leonard. Someone in the chat put up the right thing. Ammonia turns damp red litmus paper blue. This is the test for chlorine. And yes, you do need to know this. Oh, why did I get rid of that? You do need to know this for combined and triple. Sorry about that, guys. Occasionally, you know, I'm a little bit of an idiot.
Whenever I'm about to do something, I think, would an idiot do that? And if they would, I do not do that thing.
Okay, so let's go. How long ago was the Earth formed? Who can tell me how long ago the Earth was formed? It's actually 4.6 billion years ago. And then the percentage of carbon dioxide in the Earth's early atmosphere, we just did this in the 6 marker, decreased, went down. Which two processes caused CO2 to go down? Carbon dioxide dissolving in seawater, combustion of fossil fuels, farming of animals, formation of sedimentary rocks, volcanoes releasing CO2. What would you put for these two? Yeah, so what are we putting? Dissolved in water, Batman's secret? Absolutely, it dissolved in the seas. What's the other one? Who said the fourth one? You're absolutely right. It formed sedimentary rocks, which are carbonate rocks. So, and it formed the shells and bones. Combustion, think about that. That releases CO2. Farming releases CO2 because you've got to drive tractors and you're going to, it's a very energy thingy, and volcanoes give out carbon dioxide, so none of those because they all give it out. All right. Oh my good gosh, you do need to know that greenhouse gases are linked to climate change. You're all good with that, right? I hope you all know that the radiation is re-radiated to the Earth. Don't want to go over that. You got your carbon footprint. Are you all aware of what a carbon footprint is? Carbon footprint is like the carbon footprint of my mobile phone or my laptop is how much carbon dioxide does it release in its lifetime, okay? Your carbon footprint is how much carbon dioxide do you release? Like in terms of you're on your phone all night, you're charging your phone, you know, you get your mum to drop you at school in a car, all of that business. So it's a carbon footprint, and you can do it for people or you can do it for items as well to compare their impact on the environment. It's very difficult to actually put numbers to it. Now, I just want to run through air pollution, and this topic is really done other than the bit about the atmosphere. So let's go over air pollution. Now, air pollution, when we burn fossil fuels, anytime we burn fossil fuels, so we're talking cars, lorries, factories, we're going to release carbon dioxide. Is not an air pollution. It's a greenhouse gas. It causes global warming by trapping radiation, right? So it's going to heat up the Earth by trapping the radiation, okay? And it is methane and also H2O. They are all part of those greenhouse gases. But the air pollutions are different. These are the pollutants, the poisons. Pollution are basically, yeah, I should really call that pollution gases. That should be pollutant gases. Just shows you I'm an idiot, but you know what? We ain't got that kind of time. So pollutant gases, let me run through each one. Nitrogen dioxide is formed when in a car, nitrogen from the air, N2 and O2, go into the car. They combine on the hot car metal, and out the back of the car comes NO2. What's the problem with NO2? It causes acid rain. It is acidic. It forms nitric acid when it dissolves in water. So that's bad. Also, it has a second bad thing. If you have asthma, respiratory issues. So you can just say like asthma. All right, another pollutant gas coming out the back of cars is carbon monoxide. This one joins with your hemoglobin in your red blood cells and prevents oxygen being transported around your body, so you can't respire and you die. So this one is very dangerous. This can literally kill you. Poisons red blood cells. I'm just going to write that, okay? That is from It's called incomplete combustion. So if there isn't enough oxygen. A good sign that you've got incomplete combustion is if you see a yellow flame or black soot. So soot, this is solid carbon, just carbon particles, solid black carbon particles. These are going to cause I can't spell it, guys, respiratory issues, basically breathing problems. And now the other one I want to cover, what the earth? Oh yeah, the other one I want to cover is sulfur dioxide. Now sulfur dioxide is going to go up into the air. It's going to go into the clouds and form sulfuric acid when it mixes with water, and you're going to get acid rain. Okay, so sulfur dioxide causes acid rain. You might say, sir, how the hell do we get an S? I can get nitrogen and oxygen come from the air. They're nothing to do with the fuel. The fuel is producing that and that. How the hell are we getting an S? Because fuels contain SaH18. They're hydrocarbons. Guess what? There's some impurities. So you have sulfur impurities inside the fuel. Tiny little sulfur atoms. And of course, when we burn fuels, it's hot. They also join with the oxygen to make sulfur dioxide. So, and then they dissolve in clouds and they come down as acid rain. Why is acid rain bad? You've got to know 2 reasons why acid rain is bad. So acid rain changes pH of soil and H2O. Why is that bad? It's going to kill trees. I could just say plants, but I'm going to say trees. And it kills fish, okay, or anything in the water, because it changes the pH of the soil and the water. Anybody got any questions? Yes, also erodes limestone. Thank you, Lucas. Well done. Yes, yes, yes. OMG. Now, that's air pollution. Maybe I'll give you a little... did I write any... Hold on. Let me give you a pollution. Then I think I'm going to go through, like, potable water and stuff. And some people said they want to go through... Did I write down? No, I didn't. Never mind. What a twit. Okay, I'll tell you what I'm going to go through next, and then I'll give you some questions. So let me give you some more questions in a secondo. What's that on? All right, guys, see if you can do that one. Polymerization. Yeah, I'll do polymerization. I think it's not as bad as that. Normally it's easier, but, you know, it depends on the year. Like, if everyone thinks paper 1 was easy this year, then, you know, but normally it's easier, I think. There are mole questions come up in this, so be prepared for your mole questions. Don't be gasping. Visualize a mole question. If you're doing triple, you're going to get a 4 or 5 mark amount of substance mole question with the ratios and everything. Most methane is obtained from natural gas, which is a fossil fuel. Methane can also be produced renewably. Which 2 renewable sources of methane? Animal waste, food in landfill, nitrogen in the air, non-biodegradable plastics, or scrap iron. What are we going with, people? Anyone got an idea? Where could we get CH4 from? Because you can burn it in Bunsen burners, you can use it as a fuel. Yes. Who said animal waste? Absolutely, 1538. Boom! Yeah, you're right, animal waste. And also food in landfill. So methane is produced from rotting stuff. And, you know, it's a biofuel at the end of the day. So it's renewable because you can just get the animals to poo more. Nitrogen in the air isn't going to give you methane. It's basically nitrogen atoms. Plastics, non-biodegradable plastics, no, they're not going to release methane. They don't really break down very well. And scrap iron, that's Fe atoms. So, yeah, that's not going to give you it either. Right, what we're going to do... Couple more of these, and then we're moving on. Couple more on the old atmosphere, and then we're off of this, okay? Yeah. Petrovich is a renewable form of methane. Okay. What the hell? Why are algae less likely to photosynthesize on Titan than on Earth? I guess we had to plot something here, and I didn't bother doing that. That's a bit dumb. Percentage of the gases in the Earth's atmosphere. Oh, well, if we had to do that, it's roughly like that. Okay? It should be roughly 21 and 78, but they're going to take anywhere like, yeah, you get the idea. Why are algae less likely to photosynthesize on Titan than the Earth? So why do you think algae can't photosynthesize on the moon called Titan? Titan's one of the, like, Jupiter or Saturn's moons. Titan's atmosphere contains too little argon, too little carbon dioxide, too little methane, too little nitrogen, too little CO2. Absolutely. Photosynthesis, people. Bio. Right. Titan is warmer than the other moons of Saturn because of the greenhouse effect. How do greenhouse gases trap energy from the sun? All wavelengths of radiation are reflected back to the surface. Long wave radiation is reflected back to the surface. Short wave radiation is reflected back to the surface. Does anyone know this one? Oh my gosh. Best of Pro. It's long wave. So you might be going, sir, I don't flipping get that. Let me quickly explain. Let me explain to you why the long wave is the one that gets reflected back. Huh? So this is your greenhouse gases here. These are your like CO2, methane, etc., H2O, greenhouse gases in the atmosphere. What happens is the sun releases short wave radiation. So I'm going to give it a little yellow color because on the electromagnetic spectrum in physics, or orange, right? It can penetrate through the atmosphere. You've got to have a high frequency and be a short wave to penetrate the atmosphere. Then what happens is it's absorbed by these guys, and on the way back, the length of the radiation increases, and now the long wavelength cannot penetrate the atmosphere and it bounces back off the greenhouse gases. So this is long wave, short wave. So the radiation is short wave when it leaves the sun, but it loses some frequency. The waves open up as they lose energy and become a longer wavelength, so they can't get through. All right. Let's move on. Some people have just been asking me about fighter mining and that, so I'm just going to quickly deal with that because that's something people like to say in the chat. Fighter mining and bioleaching, and they do come up. Fighter mining more than bioleaching, but they both come up. So let me just go through these. So you have like copper ore. Now copper ore is a rock with enough copper in to make it, oh my days, economically viable for extraction. So a copper ore, what's the difference? Well, we just say, look, a rock which has enough copper in it, that rock has got quite a lot of copper in it, makes it good for extracting. Then we have low grade copper ore. If you were to try and get the copper out of this stuff, it's not viable. You're going to spend millions of pounds smashing that rock up and getting the copper out, and at the end only have a little copper. So we've come up with some ways to get the copper out where we don't have to spend lots of money, and it's much better for the environment, because if we use low grade ore, we conserve these for our grandchildren, so they get to have this copper. So we should be using this. These are the two ways, and it is to ensure, we call this sustainability. So sustainability is to use this because it means it is sustainable. This copper will be around for future generations rather than being greedy and using up all the copper. So we've got two ways. We can do phyto mining, and all you have to say with phyto mining is you're going to get a plant and you grow the plant. So we're going to say grow plant on low grade copper ore. Now ore just means rock, but essentially we're going to grow the plant on it, guess what the plant is going to do? The plant is going to use active transport and stuff, and it's going to get some of that copper inside its body. So the plant will absorb copper. So plant absorbs minerals, i.e. copper atoms. So the plant has absorbed some of the copper. What we do next is a little bit brutal on the plant. This is called phytomining. It's the plant one. We're going to set the plant on fire. We're going to burn it up. So we're going to burn this plant up. And why are we going to burn the plant up? We're going to burn it. So we burn plant, collect ashes. Now the ashes contain copper, and we're going to put the ashes in a beaker like that, and we're going to do the old electrolysis on it. So collect ashes and then electrolysis to extract copper. Now, to be honest, you've got to make a solution. If you try to do it on solid ashes, it won't conduct electricity. So really, if I was doing 4 marks for phytomining, it would be grow the plant on the ore, burn the plant, make a solution with the ashes, do electrolysis to extract the copper. Now, you can use scrap iron is also another method to extract the copper. Lovely, Lucas. Yes. Good. Now let's do phytomining. You can use displacement with scrap iron. Absolutely. Displacement with scrap iron is another way. Let's look at bioleaching. So bioleaching is slightly different. Let's check out the bioleaching. And then I'm going to do potable water and sewage. I'll give you some questions on that stuff as well. Okay, so you've got bio-leaching, biological leaching. What are we doing this time? This time we're getting our rock. It's low grade. It doesn't have a lot in it. We're going to get bacteria. This is supposed to be bacteria, right? Not very good, I know. We're going to get bacteria. So we're going to go bacteria live on rock. Basically the low grade, it's better to call it low grade ore, but it's just so long to write that out. They're going to absorb minerals. They absorb copper or any other metal, because you could get a question talking about another metal. So they absorb copper, and then they produce, this is a key word, they produce a leachate. So we don't have to make a solution this time. The leachate is a solution with the minerals in there, but with the like copper 2+ ions. So they've got a leachate. All we're going to do is use scrap iron, and we call that displacement. Iron is higher than copper in the reactivity series. It will push the copper out and you'll collect the copper on the iron. Or electrolysis. Remember, electrolysis isn't as green as possible, because it's not as green as using scrap iron, because electrolysis uses electricity. So there's a little bit of CO2 release when you produce the electricity. So electrolysis to extract copper. There you go. That's bioleaching. Right, let me give you some questions. Let me give you some questions, just general questions while I bish bash bosh. No, we don't want those ones. What is that? No. Paper plates, LCA. We'll come back to that. What's that? Water. Oh my gosh. Yeah, actually, let me see. Fertilizers. No, we don't want fertilizers. Chromatography. Oh, let's do a little bit of chromo. Oh my god. All right, let's do some chromatography and just see if you can. Do you mean for phytomining and bioleaching? So for bioleaching, the advantage is that it's a renewable process. You're using, for both of them, the same advantage. You're using up low-grade copper ore, which conserves the high-grade copper ore. So it saves copper for future generations. It prevents us having to mine and use up the precious non-renewable copper ore. So copper ores are non-renewable, and we're saving them by using bioleaching or phytomining. We're conserving them and allowing them for future generations. That's the main bit. Also, when we extract copper from high grade ore during normal mining processes, they release a lot of greenhouse gases. They have a negative impact on the environment because those processes use a big mining machinery to quarry out the rock and that. Whereas here we're using low grade ore, okay? And what you're going to do, so once again, phytomining, it's just grow the plant on the ore. It will absorb the minerals. You burn the plant to create ash. You mix it with water to make a solution, and then you do electrolysis or displacement with iron. And then with the bioleaching, you're going to use bacteria instead of plants. You don't burn them this time because they produce a juice, a solution called leachate, which will get you a mark, which contains copper. And then you just say do electrolysis or use scrap iron on them. Now, if you have a look here, I'm going to just do a couple of chromatography questions to get this one out of the way for you. And then any questions you want to ask. This is a student's chromatogram. The yellow and blue spots are very close together. Which two ways could we increase the distance? How could we make it so the yellow is there and the blue is there? What could we do that might change the distance? Allow the solvent front to travel further. Dry the chromatogram more slowly. Use a different solvent. Use a larger beaker. Use a larger spot of green ink. Very good, Lucas. We're going to allow it to travel further. And over time, the yellow is traveling more quickly than the blue. So if we give it a little bit longer in there, obviously take it out before it reaches the top, you're going to increase the distance. But the best way is to try a different solvent. And do be aware that in chromatography, with some solvents, that blue dye won't even show up because it will be insoluble and the blue dye will just stay on there, or the yellow dye will just stay on the line. The fact that there's nothing left on the line tells me that everything was soluble in the solvent. Right. Let's look at this one. RF value of a dye depends on the solubility of the dye in the solvent, the attraction of the dye to the paper, which will definitely produce a smaller RF value if the solvent and paper are both changed. Now, RF is equal to distance of dye, so how far the dye moves, divided by distance of solvent. You can count the solvent as moving the whole way and then how far that's moved. So it's the percentage of the way the dye has moved in comparison to the solvent. So what we want to do is make the RF smaller. So basically make the dye we want to make the dye not move as far. That's what it means. A smaller value means the dye has not moved as far. So yellow, this RF value will be like 0.3, 30%. This will be like 0.7, 70%. So if I want to make it smaller, I want it to not move as far. The dye is less soluble in the new solvent and less attracted to the new paper. That's kind of a double-edged sword, that one. I'm not sure about that one because it's saying it's less soluble, but then it's in the new solvent, but it's less attracted to the new paper. That means it's going to move about the same distance. The dye is less soluble in the new solvent and more attracted to the new paper. That one will definitely, it's basically sticking to the paper and it doesn't want to go in the liquid, so it can't move, right? The dye is more soluble in the new solvent and less attracted to the paper. No, that one's going to move further because it's more soluble and it don't want to stick near the paper. So it's going to be this one and this one. The dye is more soluble in the new solvent. So it's more soluble, but more attracted to the new paper. Oh my gosh. Oh, it's only one box. So yeah, we've already done it. I thought it was tick 2 boxes. Yeah, it's already that one. Oh my gosh. What are we doing here? Ethanol removes grass stains from clothes. What type of substance is ethanol when used to remove grass stains? What do you reckon? Excellente. Boom! It's acting as a solvent. Right. 2 students investigated dye in a food colouring using paper chromatography. Each student did the investigation differently. RF values they determined for the same dye were different. So they got 2 different RF values for the dyes. How did the students' investigations differ? So they did the same dye, like Keith did it with an orange and Bill did it with an orange, and both of them, it moved different distances. Why? They use a different length of paper, a different time period, different size beaker, or a different solvent. What do you reckon? Yeah, different solvent. Yes. One box only. And then for this one, paper chromatography involves a stationary phase. What is the stationary phase? It is the paper. Absolutement. Only a couple more of chromatography. Then we're going to disc chromatography and we're going to move on to water and have a look at the old lovely jubbly water. We're going to do potable water and wastewater treatment after this. So, a student investigated the colours in 3 flowers A, B and C using paper chromatography. Over here, have a look. The colours are soluble in ethanol, but insoluble in water. This is the method they use. Place ethanol in a beaker, add the flour, stir the colours, dissolve in the ethanol, filter the mixture, put the spots of coloured filtrate on the chromatography paper. How could the student obtain a darker coloured solution? 2 boxes. Crush the flour, filter the mixture 3 times, use a large beaker, use more ethanol, use more flowers. Yeah, I think you're right. Last 2. More of the solvent and more flowers will give us a darker colour. Larger beaker, definitely not. Filtering the mixture 3 times is just removing the solid bits. It doesn't make it darker. That one, well, crushing the flour might get more of the extract out of it. So it's possibility. What 2 mistakes did the student make? Okay, the student has made 2 mistakes. What if they made a mistake here? Lid looks good. Beaker, chromatography paper, start line in ink, water. What's the issue? Yeah, they've drawn the start line in ink. We should always use pencil. So that's a mistake. No, that's good. That's a good thing. That's good. So use a lid. That's good. It stops evaporation. Use water. They told us up here it's insoluble in water. So that is a mistake. Why? Because they told us here it doesn't dissolve in water. So you can't do chromatography if all of it doesn't dissolve in water. Right, last chromatography one, I promise. Then we're going on. So, another student sets up the apparatus correctly. Figure 3 represents the student's results. What 2 conclusions can be made from figure 3? Tick 2 boxes. Flower A contains a single pure colour. Flower A and B contain the same colours. Colour in flower C. Oh, the colour in flower C is a mixture. The colour in flower B was the least soluble. 2 of the colours of the same RF value. Let's go down. Does flower A just contain 1 colour? I would say yes. Look, there's only one thing in it. Do A and B contain the same colours? No, if they contain the same colours, they would move the same distance. They are 2 different substances with 2 different solubilities and affinities. So no. Flower C is a mixture. Yes, because it has 2 or more, not chemically bonded. Yes. Okay, right. Let's have a look. Right, guys, we're gonna do some potable. We're gonna go through potable water and sewage treatment, and then I'm gonna give you a load of questions on those. So these are very popular to come up in your exam. So we're gonna go through a whole bunch of questions on them as well. We're about 15 minutes. So, yeah, if you want to get off and get to bed, I don't blame you. You want to be up nice and early, but let's have a little look. We are going to look, first of all, at potable water. This means it's safe to put in a pot. So it's drinkable. How do we make water drinkable? Because where do we get the water that comes out your tap? Well, we get it from the groundwater and we get it from surface water. So, first of all, we get surface water and we get ground water. Groundwater is trapped underground. Now, the Romans used to build massive caverns underground to store water, called aquifers. We still have those emergency stores of water in cold rock under the ground, but they naturally form natural aquifers. That's what, when you lower your bucket in a well, what you're going to. Surface water is like rainwater on the surface, right? Rivers, streams, So you get the idea, and rainwater. So we're going to use this as our sources of water. So these are our sources to get drinking water into your house. So what do we need to do next? First of all, we take a mesh and we're just going to sieve out twigs and stuff like that. We call this filtration. So this is step one. Filtration removes stones, twigs, leaves, all the kinds of things that might be in a river. Does that make the water safe to drink? No. What we're then going to do, we're also going to filter, all still part of filter. Filter, we're going to get rid of smaller bits through sand and gravel. So you have stones and sand, and that's going to filter out even smaller bits. But guess what? You can't filter out the bacteria. Remember, bacteria are microscopic. They can get through sand. So your microorganisms, your bacteria and viruses and things, they can get through. So what we're going to do last, we're going to sterilize. 3 ways to sterilize the water. Sterilize the water means, sterilize means kill. So you do need to know we want to kill the bacteria, and we call that sterilization. 3 ways. We can use O3, which is called ozone. Now ozone is toxic. If you breathed it in, it would kill you. It's up in the atmosphere. It protects us from the sun's harmful rays, but it's also a little bit dangerous. It has the formula O3. It's called ozone. It will mash up them cells. We can also use chlorine, like when you go swimming and your eyes sting, that we can use chlorine. So that will kill bacteria. We put chlorine and fluorine in tap water. You can taste that nasty taste that tap water has, slightly nasty taste, is because they put chemicals in to kill bacteria. And then the last thing we can do is we can use ultraviolet light. So if your UV light is intense enough, ultraviolet light, sunlight, this is why you should open your curtains, right? If you've got your kind of room and you're always sitting in your room and it's getting smelly and you're just keeping your curtain shut, then you're not letting light in. Light kills bacteria and germs. So that is how we make water safe to drink in the UK. Bosh. Now, in some countries, they can't do that. In some countries, like if you've ever been to Dubai or United Arab Emirates, they don't have a lot of surface water. It doesn't rain a lot. They don't have loads of rivers and streams to give the population all of that water. So they use different processes. They use distillation of seawater. So they do have seas there, and you can distill the salt water. Distillation of seawater. Okay, now obviously in a hot country that's easy. In the UK we just don't get enough sun, and you'd have to spend so much energy to boil off the water. Distillation is just evaporate the water and then condense it, leaving the salt behind. I think you know that. So that's cool. You can do distillation. They also have something called desalination. Desalination as well, which means removing salt. Desalination. So these are in hot countries. They're going to use distillation and desalination, and they can even use something called reverse osmosis. Okay, they can use another process called reverse osmosis, but all of these processes, all of these use a lot of energy. Okay, so that's why water is more precious there and more valuable there. Let's look at sewage treatment. Sewage treatment is similar but slightly different. So we're going to look at sewage treatment and we're going to do some questions on it. So let's have a look at sewage treatment. Now, sewage treatment, what do we mean by sewage? We mean poo-poo and wee-wee and factory waste. Okay, so rubbish, toxic waste from factories, and poo and wee. And basically it has a whole bunch of, the first 2 steps are the same. So step 1, we call it screening. And it is very, very similar. It's very, very similar to filtration. It's basically filtration, removing twigs, stones, leaves, etc. Removing large bits. Ooh, yuck. Then we want to do sedimentation. This is the yucky bit. Sedimentation. This is where, like, if you've had a cup of tea and you've left it for a while, all the sugar and bits float to the bottom, but this time it's poo and wee and it's basically going to look like this. So not to be too gross, but to be gross. Sedimentation is going to look a little bit like, you're going to have like your, ooh, thank you, Jim. You're going to have your solid poo bits at the bottom, your solid waste, it's not always poo, but your solid waste at the bottom, and then your liquid waste on top. Now, okay, so this is where it splits. We call this effluent. Liquid waste is known as effluent, and these are treated in two different ways. And this is our solid waste, our sediment. Okay, and we're going to treat these in two different ways. This is going to do aerobic, and you have to know this. This does aerobic digestion. Bacteria that use oxygen. Okay, we need oxygen for this, and it does aerobic digestion. Now with the solid waste, we're going to do anaerobic digestion, and it actually gives us some biofuel. So we get, when we break down, or when I say we, I don't do it, but yeah, when they break down our waste, our poo, our feces, they actually get some methane out of it they can burn as a gas. So anaerobic digestion of solid waste, and that produces methane, which is like biofuel. So we actually get some CH4 out of that. So that's got a little benefit there. And it can be used as fertilizer. Yeah. You can also use poo as fertilizer. They don't tend to use human poo as fertilizer in the UK. We got strict laws on that because of various bacterias and things. We don't like to use human poo. Like using cow poo, they only eat plants. It's a little bit different than meat eating animals like humans. So we tend not to use human poo as a rule in the UK for fertilizer for growing any food. But the rules aren't the same everywhere. So yeah. Yeah, sludge. You can call that solid waste. You can call sludge. You'll get the mark for solid waste as well. You can call that sludge or sediment. Absolutement. Yes, aerobic digestion, anaerobic digestion. I haven't got space to write, but after all of that, if for some reason you want to put some of the liquid waste back into the water supply, you want to put that back into the tap water, you're going to have to sterilize it. We try to avoid that going directly back into the drinking supply. Okay, no. And I'm just going to do a couple of water questions, and then I will have a look at that before. Oh, catalysts. Very quickly, if you're doing triple, I will give you some water questions in a second. I just stumbled across this. These are very simple questions, but catalysts in catalytic converters is a mixture of three elements. I just want to quickly show you where in the periodic table are you going to find these elements: alkali metals, halogens, noble gases, transition metals. Where do we find catalysts? We're going a bit laggy. Boom! Transition metals, absolutely. Methanol is broken down in the body during digestion. What type of substance acts as a catalyst? Amino acid, enzyme, ester, nucleotide, OMG. In the human body, it's an enzyme. These are biological catalysts. Other metal ions form coloured equilibrium mixtures with thiocyanate ions. Which metal ion can form a coloured equilibrium mixture? Which of these would have a colour? Anyone know for that one? Cobalt. Who's the Don? Who's the Don Dada? Yes, cobalt, because that is a transition metal. Absolutely. Yeah. Cobalt is a transition metal. So well done, well done, well done, well done, well done. Okay. Let's just have one more little thing on, like, just a couple more of these. So I didn't go over this earlier when I was doing endothermic whatever they were, but you actually have to know this for the triples. So what is represented by label X? What is this little baby camel's hump on the energy graph? That is the activation energy with a catalyst, absolutely. So it lowers it Just 3 more on catalyst, guys, then I'm never going to talk about catalysts again. The activation energy for the reaction between zinc and sulfuric acid is lowered if a solution containing metal ions is added. What is the most likely formula of the metal ions added? What is the most likely formula of the metal ions added? Is it aluminium 3+, Ca2+, Cu2+, or Na+? Which one of these is going to lower the activation energy? Which one is going to be the catalyst? Boom! It's the Cu2+. So you're getting the coup, right? You're getting all of these right. The reaction uses a catalyst to increase the rate of reaction. Catalyst, metal oxide. Which one of these is going to make the metal oxide? Vanadium. Smacked it. Right, it's always the one in the middle of the periodic table if you're wondering how these people are getting this right all the time. OMG. 2 boxes. A nickel catalyst is used in this reaction. Why is a catalyst used? What are the 2 things a catalyst can do that will help us? I know they lower the activation energy by providing an alternative pathway, but that's not why we use them. So why do we use a nickel catalyst? That's how they increase the rate of reaction. But what do we want to do? 4th and 3rd. Yeah, we want to reduce costs. It's not going to increase the temperature. We can use less to produce less carbon monoxide. No, it's not going to affect what gets made. It doesn't affect the reaction like outcomes. So it's going to reduce our costs because we can use a lower temperature. So if you're using a catalyst, it lowers the energy needed so you can use a lower temperature and to use less energy. So these are the ching reasons why we're going to use a catalyst. Absolutely amazing. Yeah, we don't really need to see that again. That was disgusting. Okay. Now, we do polymers in 2 minutes. I need to give you a question on potable water. Very important. No. Because I didn't waste all the time. No, fertilizer. No, where are you? Where are you, water? Here we go. Let's do this question on potable water. Then I do polymerization. Sorry about that, it was a bit loud. Whoops, just made you deaf. Don't worry, if you've gone deaf, you won't be able to hear the kids crying in the exam when it's so hard tomorrow. Remember the exam? Yeah, it's gonna be difficult, peeps. But don't worry, because I'll help you with my predictions.
What's your strategy?
Don't need any.
What's your prediction?
Prediction?
Yes, prediction.
Pain.
Okay, potable water. Let's smash these out, and then I'll get to the chat, and I'll answer what things you want me to go over in the last half an hour. So I'm gonna do half an hour more, and I'll go over whatever you just call out in the chat rather than questions. Which 2 substances are used to sterilize fresh water? Yeah, it is normally easier. Yeah, you got it. Chlorine and ozone. Boom, boom, bada bada boom, bada 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 boom, bada 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 boom. Which 2 methods show the presence of dissolved solids in a sample of drinking water? I guess we could evaporate all the water and then we will see some salt, right? If you add damp litmus paper, no. Damp litmus paper will just tell you like chlorine, but that might not be a dissolved solid. Test the sample with a glowing splint. No, that's hydrogen. Measure the sample's boiling point. Why? This is, if it has a range, if it boils, let's say over, like, I'm going to say 90 to 105 degrees, then it's a mixture. So watch out for that one, guys. If it's a pure substance made of one thing, like just H2O, it will boil at exactly 100 degrees. If it's just ethanol, it will boil at 70 degrees. If it boils over a range and the temperature changes over the range, remember the temperature is supposed to stay the same during change of state. It's not supposed to boil over a range. It's supposed to go flat on the graph when you're changing state. If it boils over a range, it means you're dealing with a mixture. All right, let me just wait. How could pure water be produced from drinking water that contained dissolved solids? How can we get pure water from this? Yeah. Okay. What else? And then I'll just go through whatever you guys want me to go through. What the fudge? Listen, LCA is dead easy. If you're thinking, what the hell is an LCA, right? If you're like in a panic, life cycle assessment, what does it mean? It means, look at my pen. This is what I'm writing with on the board. Look at this pen. It's talking about the life of this pen. Where did this pen is plastic. Where did this plastic come from? I will do polymerization. Where did this plastic come from? Came from crude oil. So in order for us to do fractional distillation and cracking and then polymerization to get this plastic, we had to extract it, and then we had to turn it into the pen, manufacture it in the factory. In each stage of its life, we used energy and we produced greenhouse gases. We then had to sell it to the user. Now, while it's being used, this is not producing any carbon dioxide. So this has got quite a low impact on the environment while I'm using it. But how long does it last before I have to buy a new one? And that means they have to go back and extract more crude oil, mine it out the ground, convert it into a pen, and use all that energy again. So that how long its life is will reduce its impact on the environment. If I have to keep buying a new one every 3 months, then it's going to have an impact. So you've got to think about all those things. Then when it gets to the end of its life, where do I put this? I put this in my blue bin for recycling. But you could say a lot of the time this ends up in landfill. So it then has an impact. It has to be recycled. It has to be taken from my house in a lorry, and that releases carbon dioxide. So you get the idea. The life cycle assessment is about how much energy this uses, and therefore how much carbon dioxide and greenhouse gases it releases throughout its entire life. So let's have a little look. Which stage of a life cycle assessment would contain this information? Paper plates are biodegradable and recyclable. So if they're biodegradable and recyclable, is it at the end of its life, extracting it, manufacturing, or its use? It's going to be disposal. When you get rid of it, that's when you recycle it. Which two processes are used to make ceramic plates? Well, not galvanizing with zinc. Galvanizing with zinc, somebody talked about this earlier in the chat. If you make this bucket out of iron, so if this is made out of iron atoms, what we do with galvanizing is we look at the reactivity series and we find the metal just above iron is called zinc, and we coat it in zinc atoms. And zinc, just in case you wanted to know, is more reactive than iron. So what will happen is zinc will react with oxygen and leaving the iron unreacted and fine. And actually a zinc oxide layer, the zinc oxide layer is actually very unreactive, so it's not flaky. Like iron oxide is a problem. Iron oxide is flaky. Your bucket's going to get a hole. But if you get zinc oxide, it's completely different. It's not rust. Anywho, that's called galvanizing, when you coat something in zinc. Heating in a furnace, melting sand and boron trioxide, shaping wet clay. Does anyone know the two that are used here? Very good. Nice. Shaping wet clay and heating in a furnace. And you just got to know that's right. What are we doing? We did life cycle assessments, right? Okay, somebody said polymerization. Let me just lick through polymerization quickly then. So, yeah, not going to be on that long. All right, you've got two types of polymerization. So you have, I'm going to do polymerization. This is triple. You have addition polymerization, addition. You're taking two things or many things and adding them together to make one thing. So what we do with addition polymerization, it takes alkenes and turns them into polymers. Now, the alkenes are also known, the small molecules, as monomers, and we turn them into large hydrocarbons called polymers. Anywho, let me show you how we do that. Let's take the easiest one, and that is ethene. This is ethene. When I jam this together, I'm going to make a polymer. So this is the monomer, and it is called ethene. Oh my gosh, that's ugly. Right, so I can have loads and loads of these. So I could have like 1,000 ethene molecules, right? We just put N for lots. Then what we're going to do, I'm going to show you what to do. You get rid of the double bond. This is only for addition. You get rid of the double bond, and the next thing you do is draw two lines like that, and you draw a bracket, and you draw another bracket. You always do that, and then everything else goes inside, and this is known as polyethylene. Now I'm going to show you where it gets tricky, so bear with me, folks. And then you can put like an N there or N after. I don't think it really matters where the N goes. That is now known. You might say, but that's an alkane now, sir. It is, but we call it polyethylene. Many ethenes were put together. Okay, so you still keep the alkene's name that it came from. Now let me show you the next one. Which is the tricky one. I'd say this is the only hard one that they can give you on addition polymers. Right, here we go. Let me give you the only hard one they can do with addition polymerization. The only hard one with addition polymerization is, condensation is the harder one. I'm going to go through condensation as well in a second. Hold on, hold your horses. Right, what we're doing, we're going to do addition polymerization, and I said I was going to do a difficult one, but guess what? Why do I long everything out? Because I'm a bit of a bell piece, that's why. This is known as chloro, because it has a chlorine, and this is ethene. You could get this one, it forms a very traditional plastic. Now you do need to know about polymers, guys. I'm just really going through the skill of polymers, how to draw them. So again, look what I did. The first two things, I drew a line in the middle. I don't even have to look at that. And then all I do is smash everything else in. Easy peasy, lemon squeezy. Here's the difficult one. This, by the way, is known as polychloroethene. Now you'll know this because your plastic bag you got from Sainsbury's, Tesco's or Waitrose, that is made of PVC. And if you've got a raincoat and you were wearing one today because it was wet, PVC, polyvinyl chloride, is another name for polychloroethene. Anyway, what do I want to do? And that's because an old-fashioned name for ethene was vinyl. Right. Now, bing, boom, boom. The hardest one is propene. Check this. They love this one. All right, they're going to give you this. Now, this mashes people's heads. It's like crazy. People just like, oh my God, I don't get what the fudge is going on here. What is this? What I said fudge. Don't know what the fudge is going on here. So this is propene. Now, people get in all sorts of chaos because they don't follow the rules for addition polymers and they start doing this. No, remember the rules. 2 carbons only. Draw your brackets. Now put everything else in. So if I'm going to put everything else in, I'm going to go H. I'm going to go twist this bad boy down here, and I'm going to put that down there. Now, I could draw it out like that, or I'm just writing CH3. But you always start with 2 carbons there. Draw the brackets, then you can't mess up. Lovely jubbly. Right, that's addition polymers done. That, by the way, is propene, and that's polypropene. If you wanted to know the names, you should put an N. Well, okay, if you want to know about the polymers and the thermosoftening and the thermosetting, let me hit you with the thermosoftening and thermosetting then. Okay, so thermosoftening, thermosetting, polymerization. Essentially, you've got thermosoftening are like really long chains of polymers. But remember, polymers are simple covalent molecules with only weak intermolecular forces normally between the molecules. And these are the weak intermolecular forces in thermosoftening, softening. Oh gosh, that's not going to happen. All right, so we've got weak IMF. So they're going to be easy to overcome, not a lot of energy needed to break, so gentle heating and that will melt into a nice liquid. Then you have like thermosetting. These are going to be I'll give you an HDPE question thingy. Thermosetting is different. Thermosetting, they actually form bonds, solid black lines called crosslinks. Crosslinks between chains. Okay, crosslinks between chains. These are covalent bonds, and these are stronger than IMF. They take more energy to break. hence that has a higher melting point. Okay, so thermosetting is not going to melt. It'll probably burn before it melts. So, and it's because it has these strong cross-links, which are actually covalent bonds. Just remember that one of these chains, when I draw one of those chains, like as a squiggle, what they're really, it's one of these polymers. It's like got 1,000 carbon atoms and hydrogen atoms each line there. That's what it's supposed to represent. But it's just long to draw that out. So it's a model. Now let me give you a little question. I'm going to give you a question on that, and then I will do condensation polymerization. So let me just hit you with a question on HD, E. Where is that? OMG. Whee! Oh my gosh, what is the point if you're blind? What is the point, dude? Oh yeah, let's go. Come on, Tom. Sort it out. It's getting late. It's getting late. It's getting late. It's getting late. It's 4 o'clock in the evening and it's starting to get light. I'm going to give you a quick question on this, and then I'm going to do condensation polymers quickly with you guys. I haven't done all the triple organic and that. What can I say? You know, there's only so much I can cover, especially as I'm a waffler. So I have waffling issues. It means that I can't do a live quickly. I have major waffling issues. Actually, that's got nothing to do with what I was waffling about, high density polyethylene, but yeah, there we go. I don't need nobody, don't need no one, that's no good for me. What the hell? So this one's not really to do with the cross-links, but I've given you the cross-link one if the cross-link one comes up. But yeah, this is just one I could get hold of right now. So all you're going to do here, look, this made that so easy. All we've got to do is go smash, 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 and then you're going to put the end there. So, and that is it, bosh. Now, polyethylene is a thermo-softening polymer, suggests why polyethylene is easier to recycle than thermosetting polymers. So why is it easier to recycle, to reuse again? What is it about it that makes it easier? What would you say? Easier to remold them. Why is it easier to remold them? What is it about it? It can be melted more easily. So we could say lower melting point. Yes, it's down to the weak forces. They weren't looking for that for this one. Lower melting point, easier to remold. So it's just the fact that they've got a lower melting point because they don't have the strong covalent crosslinks. Ethene produces different forms of polyethylene. How can different forms of polyethylene be produced from ethene? How is it that we can get different types of polyethylene? What would you have to change? And you don't have to be specific. You can name anything. What would you change about a reaction? Yeah, you could say weaker intermolecular force is easier to overcome. So you could just say, name anything. Change temp, change pressure. So this is just change the conditions. Use catalyst. Remember, you've got catalytic cracking. So if you change the conditions, like use a zeolite catalyst or you use steam cracking or catalytic cracking, you're going to get different outcome. And then this one was more like just think on your feet. Why is high density polyethylene, basically, why does high density polyethylene, they're basically asking you what is density? What is density? Is essentially what this question is asking you. So all you're going to do is go, well, look, if I draw that same circle here, this one in the same this one has more mass in the same volume. So I can just say more mass in same volume. Now, if I want, I can say more atoms in the same space. Yeah, or I can say more atoms in a smaller volume, you know what I mean? So yeah, it's got more atom, bigger mass over volume. Remember, density equals mass divided by volume. So that one's quite easy. Right, yes, catalytic converters. If you're talking about catalytic converters, I don't know if catalytic converters on your course. Well, this is what a catalytic converter does. So in comes the nitrogen, in comes the oxygen into your hot car, like that, and it gets turned into NO2, right, which is bad for respiratory problems. It's going to run through this thing. This thing's worth about £700-800 on your car. Very expensive, made of platinum. It's going to run through here, and as it runs through here, it's going to reform nitrogen and oxygen. So it's made into hot, less harmful gases kind of thing. Sometimes CO2 or whatever. Yeah, okay. Oh. Right, condensation polymerization. Let me give you a quick one on give you a quick question on condensation polymerization. So, condensation. What do you think of when you think of the word condensation? What the arse? Is that 2021? That's not the trips. Oh my god, this is the problem. No. Yes, you there. Right, you went missing from me. Okay. So, hopefully you think of water. Oh yeah, carbonates. I'll do that. Let me just look at this quick condensation, then we'll do the sulfate ions. We'll do the chemical analysis. Yeah. So condensation, polymerization. Condensation just means water, so draw a circle around an alcohol functional group. By the way, that is alcohol, that is alcohol. Alcohol is OH. This, oh shit, I'm sorry. This is COOH, that is carboxylic acid. So this is a dicarboxylic acid. And with condensation, polymers, you have to have the same functional, you don't have to have the same one, but you have to have a functional group at each end of the molecule, and you remove water. This you actually don't do in, this is an A-level thing, but yeah, you don't need to point it out. That's called an acyl chloride. Draw a circle around 5 around alcohol. Right, so that was the answer there. That was the answer, alcohol. Complete table 2 to show the formula of the small molecule produced when monomer A reacts with B. So when A reacts with B, this is the tricky bit. You're going to get H2O. Why are you going to get H2O? This was a sneaky little bugger. So let me show you why you're going to get H2O. When you join these guys together, what happens is it's called condensation. So you would think that like an OH from there is going to snap off, or let's do it from here. An OH from here is going to snap off, and an H from there is going to snap off, and they are going to form H2O. Don't forget that it will happen at the other end as well. Like if we're going to join these up, so you would end up with monomer A looks like this, and it will end up, we will have that O to a C with that, and then this is monomer B. And then if you have to join two together and you're like, sir, I don't know if I've done it right. How do I know if I've done this right? You want to count, and I might do it wrong to start with, so just bear with me. Oh, there's a C and an H there. Sorry, guys. CH, CH. And then there's supposed to be a CH. That looks so ugly, man. Why did I do it like that? Never mind. Right, now all I want to do is count how many have I removed. So I need to remove, when you join two condensation monomers together, 2 H2O comes off. So let's make sure I've removed that. I've removed an OH there and an OH there. So I don't want, that looked really ugly. I need to redraw that bit. 1 second, people. I will do the sulfates. Give me 2 seconds. Oh, I've just done it just as bad. It's that time of night. Yeah, I think I've removed 2. Have I removed 2 waters? Let's just check. OH and H. Yeah, OH and H. Yeah, awesome. Great, we've removed the 2 waters. Then you can do that. That's 1 repeat unit, and you can put a little N. That's going to go on. So that was monomer A and monomer B. Just make sure monomer A, monomer B. Yeah. Now with this one, all we're doing is, instead of removing, we're still going to remove the OH. Sorry. When monomer A reacts with this, what we're going to remove this time is the chlorine and a H, and we're going to get HCl. So, yeah. Anywho, never mind. Anyway, those are condensation polymers, so they're slightly different. If you're asked to compare condensation and addition, condensation polymers, you get water released, whereas with addition, you don't get anything released. And also with condensation polymers, they don't need the CC double bond that opens up. They need to have a functional group at each end of the monomer. So notice there's one at each end. I mean, in these, there's the identical one. Right, let me do, someone was talking about the test, so I'm just going to do that before we finish up. So, and then I'm finishing up because, you know what, I've gone on far too long. What is it? Ooh, it's 9:43. So, yeah, you've only got alkanes. What I want to do, so sulfate test. So you've got your tests, right? The test for sulfate ions, right? You've got to know these ions if you're triple. You've got sulfate ions, SO4 2 minus. You've got carbonate ions. You need to know the test for those. You've got ammonium ions. You need to know the test for those. You've got chloride ions. Do you do the bromide? And oh my gosh, iodide ions. Let me have a quick look, make sure I've got all of them. And then you need the flame test, which I think maybe only 3 for you trips peoples. And you've got to do flame emission spectroscopy. I'll quickly run over that. It will only take 2 seconds, right? Yeah. And then you've just got them. Oh, and then the positive ions. Right, so let me go through these ones, right? So each of these, first of all, for sulfate ions, you're going to add HCl. So you're going to add some dilute HCl. Why? It removes carbonate impurities. So let's imagine there was some carbonates there. You don't want to have carbonates there because you might get a white solid with carbonates and it will confuse you. So add hydrochloric acid. Now there's a reason why we're adding hydrochloric acid, and it has to be hydrochloric acid. The worst thing you could add is sulfuric acid because you're trying to test, does this unknown solution have sulfate ions in? Well, it will bloody do if you go and add sulfuric acid. So don't add sulfuric acid because you just be adding the thing you're testing for. So you're going to add hydrochloric acid. And the reason is to remove impurities. And then you're going to add barium chloride, right? All chloride salts are soluble. Even lead chloride, I think, is soluble. All chlorides are nearly all chlorides. All nitrates are definitely soluble, but barium chloride. But, of course, that's going to break up into Ba2 plus ions. You're going to get a little reaction, Ba2 plus SO4 2 minus, and that is going to form BaSO4, which is a white precipitate. So you're going to see a white solid of barium sulfate. Now that is the test for sulfate ions. Any ions are going to be AQ because ions are AQ. Now we're going to look at carbonate. Carbonate's dead easy. Yeah, you're going to do the add. I'm just going to say add acid and then lime water. So we've already done that. If you add an acid, it will release CO2 and then it will make lime water go cloudy. So that one's dead easy. We don't need to worry about that. Ammonium ions. What you're going to do with ammonium ions? OMG, do you have to know ammonium ions? I don't know if you have to know ammonium ions for AQA. Hold on, let me just double check. Do you need to know ammonium ions? I don't think you need to know ammonium ions for AQA. I might be talking out my backside here. You just add a sodium hydroxide and then test with damp litmus paper and it would go blue. I don't think you need to know that. Scrap that. I don't think you need to know ammonium ions. Not 100% sure if you do. I can't work it out at this late at night. But if you do, you add sodium hydroxide. It releases NH3 ammonia gas, which turns red litmus paper blue, damp red litmus paper. Right, beware, beware, beware. Chlorine gas and chloride ions are a completely different thing and require a completely different test. Okay, so beware. This bleaches, that's a molecule, a covalent compound, that's an ion, two different things. This bleaches damp litmus paper. You need it to be damp, so hydrogen ions are about. Bleaches damp litmus paper. Okay, now chloride ions, bromide ions and iodide ions are slightly different. What you're going to do with these, you're going to add to these silver nitrate, AgNO3. Look, we're adding that, so we might as well, look, let's add an acid as well. Why do we add an acid? You need to know about adding acids to remove impurities. Do not add HCl. You see I said add HCl there. Do not add HCl there. Remember, we're trying to find out what is here. If you go ahead and add HCl, you are adding chloride ions. So you're screwing up your test because you're adding the thing you're trying to check for. So only add nitric acid, add silver nitrate, and what you're going to get is you're going to get silver ions in a reaction with chloride ions. They're both aqueous. They're going to form silver chloride, which is a white solid. Okay, that's white. If you're going to do Ag plus bromide ions, you're going to get a cream solid, and it's cream. And then the final one is iodide ions are going to make a yellow solid. Now, I think of it as milk, a glass of milk that's going off. I've called the milk off test. And you just go down the halogen. So chloride ions go white, bromide ions go cream, iodide ions go yellow. Right. This is triple. Yeah, this is triple. This is triple, this bit that I'm doing. The live is finishing very soon. Very, very soon. Very, very soon. Very soon. Very soon. Because it's bedtime. Now, I just want to rinse through quickly on the old flame tests. Again, this is triple. This is triplicious. So, you've got your flame test. What you're going to do is you can either take powder or you can take your unknown solution. You can put it on a platinum wire, which has a high melting point, and platinum wire, or you can use nichrome. They do not give off a color when you stick them in a flame. And which bit of the flame do you stick them in? You're going to stick them in non-luminous, the colorless part of the flame. Otherwise, if you stick it in the bright blue bit, you can't tell what color flame comes out. Now, you do need to know that sodium ions give off a yellow flame. Potassium ions, you can say lilac, purple, pink. I say purple normally. Calcium ions go brick red. What does brick red mean? It means orange red, but you can say brick red like the bricks in a house. You can say lithium ions is blood red, crimson, so it's just red. How many other ones do you need to know? Oh, copper ions is the last one you need to know for AQA, and people call it blue-green. Okay, kind of greeny blue. Now, make sure you dip it in acid in between each one and then wash it with water so there's no ions from the previous test. Otherwise, they will mask your result. Now, what happens is we can do some metals give no color. So Mg2 plus, calcium does, but Mg2 plus and aluminium 2 plus, we need to know about the other tests you can do, and of course iron 2 plus, etc. All of those ones, there's another test. So the other test for metal ions is add NaOH. That is called sodium hydroxide solution. Now, you do this because iron does not give off a color. So Fe2 plus ions, transition metals, come in two forms, so they test you on that. It's going to react with two hydroxide ions and make Fe bracket OH2, and that is a solid and it's green. Now, transition metals form lovely colored compounds. That's why these guys are in this part of the test, because we can get a color. Now, this one is going to react with three OH ions because it's Fe3 plus. And by the way, this is all going to be aqueous, those guys over there, and that is going to be brown or red. Same color as poo, because poo contains iron 3 plus ions. Same color red as well, because your hemoglobin has that in. I know yeah, anyway, enough of that business. These are AQ. So you need to know those. Now, copper is exactly the same as the flame test. Someone was like, why bother? Why bother with this? Because it gives you the, like, you can already find this out from a flame test. I get these are colorless and don't give off a flame color. So I get that, but come on now. Sort it out. Why do we have to know copper as well? It's pointless. And copper is blue, the same color, blue-green. Copper sulfate, you know that one. So copper generally is either going to be blue or green. And this one is blue-green. It's copper oxide, but blue-green. Yeah. Now, other one. You do need to know that aluminium, OMG, this is long. Aluminium is going to be, yeah, you get the idea. It's going to be OH3. I think I'm going to kill myself if this goes on anymore. That's white. Here's the issue. Look at this one. They could ask you this one. Could get a 6 marker on this one. So watch out. Magnesium is white. How are we going to tell the difference? They form a white solid. If you keep adding sodium hydroxide, the aluminium one will dissolve. It will go white, then dissolve. Aluminium hydroxide will go white. Then if you keep adding sodium hydroxide, it will dissolve, okay, in excess. Now, calcium, they might say you have calcium ions, aluminium ions, and you have magnesium ions. All 3 of these form a white solid with sodium hydroxide. They might say, how can we distinguish between them? So what we would say is, well, do a flame test on them. The one that gives the red brick is calcium. Then add excess sodium hydroxide. The aluminium will go white and then colorless, whereas magnesium and calcium will stay white. So you could get a 6 marker distinguishing between them. All right. You could do the flame test. Yeah. OMG, I'm tired now. It's time for bed. Oh, what was the one other thing somebody said? Somebody said one other thing. Some other thing. Oh, very quickly before I shoot off. Oh my God, I've got 6 minutes. Then I'm ducking out of here, folks. If you're doing triple, you need to know about flame emission spectroscopy. Flame emission spectroscopy. Basically, all you're going to do, each ion will emit different wavelengths of light, and all you've got to do is match up the bands. So which 2 metal ions are found in the mixture? Well, you just got to match it up. So that line, oh, could be lithium. Could be lithium. Let's check it out. Oh. Yep, it's lithium. So look, it's lithium. There are lithium ions in there, but it's not just lithium. Who else is in there? Let's find a bit that wasn't matched with the lithium. Who is the other one that is in here? So we know that lithium matches, but what about there? It looks like it's going to be sodium, folks. I think those 2 lines are from sodium, and then this whole little block here is from sodium. So it is lithium and sodium ions. So that is flame emission spectroscopy. You get different patterns. What do they emit? You fire wavelengths on them and they emit electrons, and when the electrons fall back down they give out energy, and you can measure the wavelengths and you get these different spectroscopies. Oh yes. Sorry, let me do that one, the anhydrous, before I chip out. Yes. So this is for pure water. So water, all right, you got this chemical. You all know what that is. That is copper sulfate. Now, copper sulfate can come like this, where it's lovely and blue. And we call this hydrated copper sulfate. Why hydrated? Hydrated copper sulfate. Now, if I show you what that actually looks like, copper sulfate actually comes with a little ting there and 7 H2O molecules. So what does that mean? Well, copper sulfate, when you see it blue, it has H2O surrounding it in like a ratio like that. It's not always 7, sometimes it's 4, sometimes it's 5, and we call this hydrated copper sulfate. Okay, so that's hydrated version. Now, why is that useful to us? Well, if we take anhydrous, and I'm feeling a bit anhydrous right now because I haven't had a drink in ages. Anhydrous means without hydrate, so without water. Anhydrous copper sulfate is a white powder, and it's just like a white powder like that, and there's no water around it. So the test for water: take some copper sulfate, heat it in the oven for a little bit, make it go white, and then if you add a drop of water, bloop, it's going to go blue. It's going to become hydrated copper sulfate. So the test for water is to add water, goes white to blue. Now there is also something called cobalt chloride paper that goes pink, blue to pink or pink to blue, one of the two. I don't even know if you need to know that. 6, 7. All right, I'm off. Take care, guys. I will be back. Yeah, hydrated is blue, dry is white. That's right. Anhydrous is white. Okay, I'll be back on Sunday night for a bit of physics for the final time. Ooh. Here we go. Got a little question on this. So it's about, this is the, Sugar Ray Leonard. The word equation for the reaction: hydrated blue, anhydrous white, plus water. So you heat it and drive it off. Okay, what name is given to the hydrated copper sulfate? Catalyst, element, product, reactant. Easy peasy, lemon squeezy. This is the reactant, these are the products. What does the symbol mean? Reversible. Oh, you're going to smash it, guys. Good night, and yeah, enjoy. And yeah, nice one. Thank you for showing up. Nice. So, yeah, what can I say? You guys are going to smash the exams.
I've had training. The training is nothing.
That's right. So, yeah, what can I say? Don't forget to hit the like on your way out.
If you push the button.
Like me.
Would you like it?
Like.
Do it. Do it. Do it.
Okay, guys, it's over. See you later.
You're still here? It's over.